The minimum weight spanning tree problem that we talked about last time was an example of an optimization problem. It wasn't just our goal to find some spanning tree of a graph, which would be more of a search problem. We wanted to find a spanning tree that optimized particular criteria. We wanted a spanning tree with the minimum total weight. And of course, the main results out of the last lecture were that we developed algorithms that solved this optimization problem. And we're not actually done with that idea yet. We're going to see in a few lectures some other graph-based optimization problems and algorithms that solve them. Today I want to talk about optimization again, but from a different angle. So instead of developing algorithms that solve an optimization problem, I want to use optimization techniques to create algorithms. I want to talk about some cases where we can define a problem that admits a recursive decomposition, but where writing a basic recursive algorithm to solve it ends up being too slow. And we'll see that if we perform some optimization techniques, if we analyze the problem using optimization techniques, we can develop an algorithm that's a lot more efficient. The issue with this topic, though, is that the name, as you can see, is dynamic programming, which, sounds pretty serious and exciting, and to an extent, that's sort of the bane of my existence. So as a student, I remember covering the topic of dynamic programming in my algorithms course, and reading the chapter in the textbook about dynamic programming, and then being able to memorize some details for a final exam, walking out of that exam and having pretty much no idea what the term dynamic programming meant. And the reason for that, which we'll see in about 30 slides or so, frankly, is that the term dynamic programming is sort of a made-up term. And what I've found is that because it's sort of a made-up term, nobody can quite agree on a consistent definition for as far as the term dynamic programming applies to computer science. This isn't helped by the fact that the word programming shows up in the name, which sort of implies that this technique is inherently a computer science technique. That is, we all know what the word programming means, don't we? It actually turns out that we don't. And so it turns out that the dynamic programming that we are going to apply is actually an optimization technique that we are going to use to create algorithms. It's not an optimization technique that can only be used to create algorithms. It actually has a variety of other applications beyond computer science. And so that puts me in the weird position of having to spend quite a bit of this lecture trying to define this term so that when we use it, when we derive algorithms using this optimization technique, we have some idea about where the actual dynamic programming took place. But first, I want to talk about the Fibonacci sequence again. So I don't think we've seen the Fibonacci sequence since way back in lecture 8 when we were talking about recurrence relations. And one of the reasons why it's a good thing to talk about in the context of recurrence relations is that the Fibonacci sequence itself is fairly natural to define. The first two values in the sequence are 1. Now we can number the sequence however we want, but I've chosen to call this value f of 0 and this value f of 1. The first two values are 1, and then every subsequent value is computed by adding the previous two values together. So 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, 3 plus 5 equals 8, and so on. And this admits a pretty natural recurrence-based definition of the Fibonacci sequence. One thing that we should be careful of right now, that I'll come back to in a few slides, is that there's no requirement that I define the Fibonacci sequence with this recurrence, although it does feel like the most intuitive way of defining it. And certainly in the context of talking about recurrences back in lecture 8, it made sense to do that. It turns out there is actually a closed form for f of n, and there are other recurrences that you can use to describe the Fibonacci sequence, some of which might result in better algorithms for the way that we're about to treat it. But I want to talk about the original recipe Fibonacci recurrence right now. Now, back in lecture 8, the reason I brought this up was that this was an illustration of the type of recurrence that we would rather not find a closed form for ourselves. That is, there is a closed form, and in some other course, I suppose we could talk about how to derive such a thing. But for the sake of analyzing algorithms, where we care about asymptotic stuff, we didn't want to find a closed form for this, because maybe if we were thinking about the Fibonacci sequence, we only care about some asymptotic result. Like, for example, do the Fibonacci numbers increase, let's say, more or less exponentially or not? Or do they increase proportional to some polynomial in n? We don't need a closed form to do that. I want to bring it back now, basically for the same purpose. That is, I brought it up in lecture 8 as a way of showing that some of the techniques that we use are overkill for some of the things that we work with. We do not want to have to find a full closed form for this recurrence because that would be a bit of a mess. I also want to show now that strangely the Fibonacci sequence, which is relatively simple, gives rise to this sort of weird dilemma. So I can compute Fibonacci numbers using this sort of obvious recursive function. That is, I can basically take the recurrence and translate it into code, which is all well and good. The Fibonacci sequence is a pretty straightforward sequence to describe, and it appears to be a pretty straightforward sequence to evaluate. And as I said, it seems like we keep bringing the Fibonacci sequence in this course as a sort of a way of spoiling the party. And it's going to do that here too, because it turns out that this recursive algorithm, although it does evaluate the Fibonacci sequence, it does so very slowly. And you can try this out. So, for example, if you plug this in, like write a quick Python function or something that evaluates this using this recursive method, and then go and try and evaluate something like f of 20 or maybe f of 30, you will notice that you are kept waiting for a while. Because for some reason, although this is a sort of natural translation of the recurrence into a recursive function, it takes a really long time to evaluate. Okay, now that fact by itself isn't too exciting, and it isn't necessarily the end of the world, because we know already that there are plenty of problems that appear to be simple and yet turn out to be computationally quite difficult. One of them that comes to mind, for some reason, is the subset sum problem from back in lecture 12, or maybe the partition problem. So two of those problems derive from our antique scale, where we notice that although it seems like the problem itself is sort of intuitive, and it seems like a natural extension of some other easier problems that we covered, when it comes time to write an algorithm, the best that we can do is exponential. So I guess it's not the end of the world if it turns out that evaluating the Fibonacci sequence is really slow using this recurrence. If you wanted to, you could prove that the running time of this algorithm is big omega of 2 to the n over 2. Which is, of course, exponential. It's not 2 to the n. It's actually, if you break it down, it turns out this is actually root 2 to the n. But it certainly is exponential growth. And I bring this up because it turns out that the actual growth rate of the Fibonacci sequence is, of course, not root 2 to the n. It's something else, something a bit bigger than root 2, but something we'd rather not work with directly. And that's for the same reason as we mentioned back in lecture 8, which is that for the sake of proving that this algorithm is pretty slow, if we can show that it's big omega of some exponential function, I think that does the trick. We don't need to show exactly which exponential function it's big theta of. We just need to show that it's definitely bigger than some other exponential function. Okay, so too bad. Even though the Fibonacci numbers are often used as a sort of introductory example, maybe even in first-year programming, it turns out that evaluating them recursively takes a long time. Okay, well, end of story, I guess. Well, not quite, because there's this. So here's an iterative algorithm, and this iterative algorithm is able to evaluate the Fibonacci number f of n in linear time, in big theta of n time. And it does so with a pretty obvious mechanic. In fact, I might use an example like this, so an algorithm that computes Fibonacci numbers iteratively, as an early example of doing something non-trivial with loops in first-year programming, which is sort of weird. And when I teach first-year programming, I mention this, that a lot of people like to bring up Fibonacci numbers as an introductory example of recursion, which sort of seems to defeat the purpose, because as we saw a minute ago, the recursive evaluation of Fibonacci numbers is very slow. So if you want to make the case to people that recursion is pretty cool, you don't really want to do it with Fibonacci numbers, because there's an iterative solution that's way faster, and the recursive solution is embarrassingly slow. That is, because this is going in linear time, you could compute thousands or millions of Fibonacci numbers in the same amount of time it might take to compute the value, f of 30 using the recursive implementation of the recurrence. Okay, so I want to briefly describe just the notation I've used here. I don't think that it's like above our level to compute Fibonacci numbers iteratively or anything. Like that is, I understand that everybody watching this could easily write pretty much the same function I've written here. I just want to make it clear what my variable names are. So basically, what I'm doing at each step of this is I'm keeping track of the current Fibonacci number that I'm working with, and I keep track of the previous one. So suppose the previous one is 2 and the current one is 3. At each iteration of the loop, I compute the next Fibonacci number by adding the previous one and the current one together, and then I just shuffle them along. So I set the previous one to be what was previously the current one, and the current one to be what was previously the next one. And then the idea is at the end of the loop, I return what I'm holding as my current value. Okay, so that's why I'm using my variable names next, previous, and current. I considered doing something like call my variable previous 1 and previous 2, but I felt like that was actually maybe more confusing than doing it this way. In any event, what I'm doing here is I'm basically applying the same insight as the recurrence. I'm just doing it in a certain order. And that's the dilemma that we need to start this lecture. Ultimately, that's the problem we are trying to solve in general, is this weird confusion between having a recurrence, implementing it recursively and having it end up being very slow, but finding an iterative implementation of basically the same recurrence and having it be pretty fast. So the observation I want to make right off the bat here is that although this iterative algorithm is certainly different, that is, I don't see any recursive calls or anything, and certainly it's not a recursive algorithm, I mean, like, it is a different style of algorithm, fundamentally I claim this algorithm is based on the same strategy as the earlier recursive algorithm, which is to say that a standard original recurrence for Fibonacci numbers says that f of n is equal to the sum of f of n minus 1 plus f of n minus 2. And in my recursive algorithm a minute ago, it was pretty obvious that I was implementing my algorithm to exploit that recurrence. I mean, there it is there. Look at those recursive calls. I claim that this iterative algorithm is doing the same thing. It is computing each value f of n by summing up the previous two values. In other words, this iterative algorithm isn't using some other trick to compute the Fibonacci numbers. It's using the same trick, it's just doing it in a more clever way. And the reason I want to make that distinction is that, of course, we've seen plenty of cases where an iterative strategy might be faster than a recursive one because the iterative strategy can exploit some trick that the recursive one can't. So there are ways to do that for the Fibonacci sequence. So I've mentioned already that there is a closed form for f of n. And of course, closed forms are something you could easily evaluate in a non-recursive algorithm, and it shouldn't surprise us that evaluating a closed form instead of a recurrence might require less work. There actually are also different recurrences. There are ways of computing f of n faster than in linear time in terms of n using some other recurrence. There are recurrences that don't go down in steps of 1, but go down in steps of, I don't know, give or take like n over 2 or something. And I guess, obviously, it wouldn't be surprising if I wrote an iterative algorithm that used a different recurrence or a closed form, that would be faster than my recursive one, because it's using a different technique, and maybe the technique it's using is more efficient. No, but that's not what's happening here. Here, I have an iterative algorithm that's using the same computational strategy as my recursive algorithm, it's just doing it in a way that results in greater efficiency. And I think that that's sort of weird. I think that that's something that we should investigate, because all this time, we've worked with a lot of recursive algorithms, and maybe due to some weird coincidence, every time we come up with a recursive algorithm for something, it does seem to end up being better or at least equal to its iterative alternative. There are some applications we've seen, and again, I for some reason think back to subset sum from lecture 12. There are some applications that we've seen where the only solution that seems to make any sense is basically a recursive one, the only algorithm that seems to be natural. And there are plenty of other cases where we've seen iterative algorithms that can exploit some different technique to be fast, but we haven't really addressed this situation of what if I use the same technique in some iterative algorithm and it ends up being more efficient just due to the way that I structure the execution of my algorithm. So the question that I want to ask right off the bat, so what I want to do to lead us into our topic for today is to ask the question, why is this recursive algorithm so bad? Well, because it's exponential. No, that's not what I mean. Of course it's exponential time. Why is this exponential time and the iterative version that uses the same computational strategy ends up being linear time? I want to analyze that. Maybe it's sort of obvious. I don't know. So I think there are people that would look at this problem and say, well, clearly, if you look at those recursive calls, you're going to see ... Maybe it's obvious, maybe it isn't, but I actually think we should try and break it down and analyze it. And it's true that the conclusion we reach on the Fibonacci numbers is going to be sort of, I don't know, I don't want to say obvious, but once we get there, it is going to make some amount of sense. It's going to be the kind of conclusion that isn't really that surprising, but I feel like using this as our example, because we're familiar with Fibonacci numbers, and frankly, the functions involved are pretty simple, using this as our example, I think is a good way of bringing up the type of analysis that we're going to need for some more complicated problems later in this lecture and in the next lecture. Okay, so let's do this. Let's formally analyze the recursive structure of the recursive algorithm. So when I want to compute f of n, I make a recursive call to compute f of n minus 1. And we map this out as a tree because we know that the recursive call for f of n minus 1 fully completes before I come back up to the call for f of n, and then I make a recursive call for n minus 2. That's the way recursive calls work. They're independent of each other. Okay, so inside of my recursive call for f of n minus 1, I make a recursive call to compute f of n minus 2. That's interesting. So I then fully compute f of n minus 2. I fully compute f of n minus 3. And I'm already noticing there is some sort of weird, disturbing duplication in this tree. So notice that while computing f of n minus 1, over here, in isolation, I choose to fully compute f of n minus 2 with a recursive call. Okay, well, fair enough. That's how recursion works. But then later, I jump back up to f of n, and then the other half of the recursive algorithm for f of n is to make a recursive call to compute f of n minus 2. What that's telling me is that I fully compute f of n minus 2 twice in this recursion tree. And it does seem as if an algorithm is a bit too slow and there's no obvious reason why, and I find some duplication, some redundancy, well, certainly that's a good candidate for what I should blame. Now, the question then is, why is this happening? So that is, why haven't we had to confront this problem before? And what I will observe is that because of the way the Fibonacci sequence is defined, or at least the way this recurrence works, it happens to be that when I want to compute f of n minus 1, one of the things I need, one of the dependencies, is also a dependency, a direct dependency of f of n. In other words, what I'm solving here aren't just a bunch of subproblems that I'm solving recursively. Specifically, they are overlapping subproblems. The two recursive calls made from level n, so f of n minus 1 and f of n minus 2, are performing overlapping computations. And that's sort of bad news, because if I see redundancy showing up there, then there could be redundancy elsewhere, and in fact there could be a lot more of it. And so if I look, for example, at f of n minus 4, notice how there are a whole ton of calls to f of n minus 4. And of course the tree keeps going below here. I just didn't draw all of the other levels of the tree. But depending on how deep the tree is, depending on how large the value of n is, there could be tons and tons of duplication. Currently, if we just look at the first 4 levels of the tree, so down to depth 3, I can already see 4 different independent full recomputations of f of n minus 4. And in fact, we might notice that this isn't even all of them, because if I look at this computation of f of n minus 3, one of its recursive calls is going to be to compute f of n minus 4, which means that as part of computing f of n, if I use the basic recursive algorithm, a pure recursive algorithm based on the recurrence, I'm going to compute f of n minus 4 fully from scratch 5 times. And if I compare that to f of n minus 2 or f of n minus 3, so f of n minus 2 gets recomputed 2 times. F of n minus 3 gets fully recomputed, I think, 3 times. F of n minus 4, as we saw, gets computed 5 times. And, you know, it doesn't look good for f of n minus 5, because I can already see 3 calls to f of n minus 5 this high up in the tree, but I know that each of these f of n minus 4s is going to contain a call to f of n minus 5, and so if there were 5 recomputations of f of n minus 4, the number of computations of f of n minus 5 is going to be larger than that. What this is sort of hinting is that as I go down the tree, the amount of duplication is going to compound, and I think it's going to compound exponentially. And so this is not something that we're really used to, because we've worked with recursion a lot before, and I guess we can classify the types of recursive algorithms that we've seen already or worked with a lot as being either branching recursion or non-branching recursion. And I'll just sketch out the difference. For the sake of this lecture, all we care about is the branching kind, so I'm just going to sketch out the difference so that we know the difference and then ignore the non-branching kind. Consider that we're searching a sorted array, and we're using binary search. Okay, to use binary search recursively on a sorted array, we figure out which half of the array contains or might contain the value we're looking for, and we recurse only into that half. In other words, at each level of recursion, we only make one recursive call. And we can see that the recursion tree we end up with from this style of recursive algorithm is pretty boring. That is, it's pretty much just going to be sort of a glorified linked list for the most part. On the other hand, if we think of an algorithm like merge sort, okay, let's see if we can draw the array a little bit better there. If we think of an algorithm like merge sort, I split the array in half and then I make two recursive calls. I make one recursive call on, let's say, the left-hand side and one recursive call on the right-hand side. Notice that, so this is, I call this a branching form of recursion because I'm making two recursive calls, and therefore if I draw the recursion tree, it looks more like a binary tree. And in general, branching recursion could have ternary trees or whatever. The number of children of each node could be more than two. It doesn't make much of a difference. What I care about for the sake of this example is because my Fibonacci sequence is being computed with branching recursion, I guess we shouldn't be comparing it to non-branching recursive algorithms. So if we go and think about branching recursion that we've done before, for the most part, so most of our previous experience, and the exception to this is also back from lecture 12, from our discussion of exhaustive searches. One case where we didn't work with this so-called divide and conquer strategy would have been computing the answers to subset sum and partition back in lecture 12. But otherwise, all of the branching recursion we've done, so for example, merge sort or quick sort, has been in the context of what we call divide and conquer, where one of the key points, of course, is the word divide. I take my original array with merge sort, and I divide it into two non-overlapping pieces, two disjoint subproblems. Sort the left-hand side, sort the right-hand side. And of course, the left-hand side and the right-hand side do not overlap. I've cut the array in half cleanly. And that means when I recurse down either side, I don't have to worry about the overlap that I'm seeing in this Fibonacci number recursion tree, where the same subproblem shows up twice, or more than twice in the case of things like f of n minus 4. So we've seen this branching recursive structure before, but pretty much always in the context of divide and conquer algorithms. If you think of other types of recursive algorithms that we've done that have branched, so even things like tree traversals can be viewed as a certain form of divide and conquer algorithm, they still branch into disjoint cases. So if I'm looking at the two different subtrees below a node in a binary tree, well, those subtrees, of course, are going to be disjoint. And therefore, if I recurse into both of them, I don't have to worry about some sort of weird interference effect like what I'm seeing in the recursion tree for Fibonacci numbers. And I'll take a moment here to observe that maybe the reason we haven't seen this more complicated recursive case where there's overlap isn't so much because it's uncommon or obscure, but just because of the way that, courses tend to work. That is, this is an algorithms course, and we've been working our way up from relatively simple or relatively ubiquitous algorithms, and maybe for my own convenience, I only covered algorithms that were sort of easy to describe recursively and fell into a convenient divide and conquer pattern. Because if my goal is to convince you that recursive algorithms are great, wouldn't I choose recursive algorithms that are sort of simple and don't put us in this situation? That's one of those things you always have to think about when taking a course in something, is that the topics of the course have been curated by somebody for some reason. So why are the learning outcomes the learning outcomes they are? Or why are they in the order they are? Well, part of that could just be that you need to survey a certain set of topics, but part of that could frankly just be for the convenience of offering the course. So a question we should ask ourselves is whether this situation really is that uncommon. Certainly the Fibonacci numbers are a bit of an obscure use case, and if we really want to compute them, we could use the iterative algorithm. But the argument I intend to make today and in the next lecture is that this pattern, this overlapping subproblem issue, does actually show up a lot in practical problems, and that maybe the reason we haven't seen it so much this far in the course is because we've been working with a lot of problems that are a little bit contrived, that happen to be sort of best case scenarios that break down really evenly, basically for our convenience. And it's time to rejoin the real world. Okay, so if we take a look at the recursion tree, let's say for f of 5. So let's look explicitly at a recursion tree for a small value of f. If I look at that, notice how I go down and make my recursive call for f of 4, I make my recursive call for f of 3, but way down below the call to f of 4, I notice this subtree for f of 3. And the same subtree is duplicated over here below the call to f of 5, which means I am fully recomputing this non-trivial thing twice inside of my recursion tree. And the value of n here is pretty small. This is just f of 5 that I'm doing this. Notice also that f of 2, the complete tree for f of 2, shows up 3 times. And so we can actually see this compounding effect directly, even for small values of f. Now, it's also true that the base cases show up over and over again. And yes, that is an example of duplication. I'm not as worried about that because I know that the base cases themselves don't really involve any computation. So although, yes, having a lot of them show up here does involve some work, it's minimal work. And for reasons that'll become clear later in the lecture, it turns out that returning the value 1, which is what these base cases do, doing that over and over again doesn't really hurt us that much. Because whether I'm, in air quotes here, recomputing the value of 1 versus simply loading it out of memory because I've stored it from earlier, that doesn't really make much of a difference because, computing the value 1, returning the value 1 doesn't take very long. What I could do here also, because the goal of drawing this tree out is to model the different subproblems, the different dependencies of each problem that I'm solving recursively. Because my ultimate goal, the optimization process I talked about at the beginning of the lecture, is to see if I can find a way to restructure my recursive computation to avoid the redundancy. So the graph that I've drawn here, oops, I shouldn't have said graph there. I might be getting ahead of myself. The thing that I've drawn here, maybe we can call this thing a tree still. The tree that I've drawn here is a representation of the subproblems that I'm solving. And for the sake of modeling the behavior of those subproblems, I'll draw some arrows here. Now, the direction in which I draw the arrows is my choice. That is, there is a completely valid argument that I completely agree with for why I might want to draw the arrows pointing downwards instead. And I have a bit of an ulterior motive here. So the idea is I'm going to draw along the edges of this tree, which previously I just drew the recursion tree like this, I'm going to draw arrows to indicate the direction of the dependency relationship. In other words, I can't do f of 4 until f of 3 and f of 2 are ready, until both of those results are ready. In other words, you can think of the value coming out of f of 3 sort of feeds into the value for f of 4, and the value for f of 2 sort of feeds into it. Now, there's a different school of thought that might do the same modeling I'm about to do, but draw the arrows in the opposite direction. So they might write, instead of f of 3 points to f5, they would say f of 5 points to f3, because f of 5 needs the value of f3, or f of 5 makes that recursive call. I don't terribly care for the latter argument about it making a recursive call, because maybe in our optimization, as we rearrange these subproblems, we don't use recursive calls. So I don't want to think about just recursive calls. I want to think about which different values of f need which other values of f, or which ones, like if I look at f of 4 or something, which values use the value of f of 4. So I have chosen to draw my arrows pointing upwards. And one of the reasons for that is that it tends to match up with some definitions we saw earlier in the course. And it'll become clear what I mean by that in a minute, because I'm about to make the transition from trees to graphs. So what I'm doing here is I'm modeling the set of different subproblems that I need to solve to get all the way up to f of 5, and I'm trying to formally model the dependency relationships between them to indicate, so I can't compute f of 5 until I have both f of 4 and f of 3. And I realized that my recursive algorithm that I was using, because pure recursive algorithms, like the ones that we typically write based on recurrences, like the one we saw earlier, work in isolation. So the recursive call for f of 4 happens entirely in isolation, external to the recursive call for f of 3. That results in this duplication. When I do the recursive call for f of 3 over here, this recursive function has no idea that I already computed f of 3 over here. So of course it has to recompute it. And I guess the first question I ask is, if I want to avoid that duplication, and I know that I have these overlapping subproblems. That is, if I'm solving f of 4 over here, and that needs f of 3, and then later I need f of 3 for something else, obviously I have overlapping subproblems. My recursive decomposition isn't into two completely independent things. Well, that means that I have this duplication, and the duplication could get worse and worse as the tree becomes deeper. And so the question is, why is it that I insist on breaking down my subproblems into this tree-like form that I get with standard recursive algorithms? Why not instead try and break my subproblems down so that each subproblem occurs only once and the dependency relationships are allowed to get a little bit more tangled up? In other words, instead of structuring my decomposition as a tree with these independent disjoint subtrees, why not instead structure it as a directed acyclic graph? In this case, I'm allowed then to have each particular subtask, each subproblem appear only once, to have only one vertex per subproblem in exchange for having the dependency relationships become a little bit more complicated. Versus our tree-based representation where a particular subproblem might appear more than once, but every subproblem is only required by one other problem, the parent of that problem in the recursion tree. In my new graph-based representation, a particular subproblem occurs only once, but may be required by a bunch of other things. And of course, there could be a trade-off there, because I guess the argument I've made in this case is if we use the tree-based representation, which allows us to have a very simple dependency structure, we end up with duplication that is catastrophic in the general sense, where if the value of n gets large enough, the duplication becomes exponential and the algorithm becomes unusable. In that case, the more cluttered structure of this sort of graph might be able to benefit us. And so the key thing here is that I haven't written any code yet. I haven't actually created an algorithm. What I'm trying to do is understand my problem. I'm just trying to model the problem in a way that leads me to an efficient implementation. And so in this representation, where I use a graph instead of a tree, each subproblem occurs only once and may be a dependency of multiple other subproblems. And then I notice that I think to myself, hey, where have I used directed acyclic graphs before? I mean, we've seen them a few times, but what was the sort of key application where you have a directed acyclic graph? What is a certain thing you can do to a directed acyclic graph that you can't do for general directed graphs? Well, I guess the answer is, if we think back, I guess that was what, like lecture 28 or 29, it was topological sorting. And topological sorting is a scheduling problem, or it can be used to solve a scheduling problem. And I realized that actually evaluating my subproblems is a scheduling problem. What I need to do is get all the way to f of 5. But I can't do f of 5 until I have f of 4. And I can't do f of 4 until I have f of 3 and f of 2. So in a sense, the task of figuring out how to evaluate all of these subproblems is actually just a different version of scheduling. And I've already represented my subproblems in a representation, a directed acyclic graph, that allows me to use an algorithm, topological sorting, that can be used to solve scheduling problems. And of course, again, all of this is just a model of a problem. I haven't written an algorithm here. Instead, I'm trying to find a way of breaking down my recursive process into a sequence of tasks that can be performed efficiently. So my observation is, if I find a topologically sorted ordering of this graph here, and observe that it's not difficult to do this. I don't even need an algorithm, because I realize that if I just evaluate each of the subproblems in numerical order, this almost seems ridiculous how obvious this is. If I just evaluate the subproblems in numerical order, that will be a topologically sorted ordering. And be careful, because what it sort of seems like is everything I just said is sort of useless in that case. Like, why bother with this graph model if I could just have done this all along? The key thing is I have a way of modeling my subproblems so that if I'm working with a problem where the subproblem breakdown is more complicated, I now have a modeling technique that helps me get to an efficient ordering of subproblems. So if I find a topologically sorted ordering of this graph, that corresponds to a way of evaluating the subproblems in the graph such that by the time I get to, let's say, f of 4, all of its dependencies will be available. I will already have evaluated them. So once I have this ordering, if I then go through the vertices in that ordering and evaluate the value of f for each one, let's say I tag each vertex with the corresponding value of f. Notice how once I get to f of 2, if I just go backwards along the edge to its inbound neighbors, it's already tagged with the corresponding value of f, so I could just then compute f of 2 by adding those two things together. If I want f of 3, well then I want to add 1 and 2. Okay, so then f of 3 would be 3. If I want f of 4, then I'm just adding 2 and 3. And again, the idea is that I could just attach the number 3 and the number 2 to the corresponding nodes. There's no need to recursively recompute them. I can just compute them and then tag their vertex with the value, which means to compute f of 4, it's very easy. I just walk backwards along the edges to its dependence, and then I add those two things together to get 5. And then finally, f of 5 is equal to 8. So I can do basically a traversal of the vertices of the graph in this topologically sorted ordering, and that means that by the time I get to a particular subproblem, I'm guaranteed that the results of its dependencies are ready for me. I do not need to do a full recursive recomputation. And what we've just done is an example of a process called dynamic programming. And I'll come back to that in a minute, but what I want to observe in the meantime is that that actually does explain why this algorithm is so fast. Because what I just did, which is tag every node with the value of f, that is one way of evaluating my subproblems in an efficient order. But I could go further and observe that as I go up the graph, so for example, if I consider these edges that indicate dependencies as also sort of indicating who needs the value, notice that once I'm done with f of 2, I'm never going to need f of 0 again. So, and once I'm done with f of, let's do f of 4, once I'm done with f of 4, I'm never going to need f2 again, because everything that required f2 will already have been evaluated by the time I'm done with f of 4. So I can even use this graph to work out which values do I need to keep around. And so if I don't want to store lots of extra values in memory, I might know that by the time I'm done with f2, I can just ignore this. I can get rid of it. By the time I'm done f3, I can just ignore this, because f3 is the last remaining outbound neighbor of f1 to be computed. And when I'm done with f of 4, I can just delete the value stored for f of 2. And really what that leads me to conclude is that the only values I ever need, so when I want to compute f of 5, the only two things I need to be storing are the two most recently computed subproblems. And that's basically what this iterative algorithm does. This iterative algorithm is one of the possible outcomes, one of the possible algorithms I might design based on the analysis that I just did. Of course, obviously, if you were asked to design such a thing, you'd probably get directly to the algorithm. You wouldn't need all of the intervening analysis. But knowing that we can do that analysis is going to help us, because some of the problems we're going to solve later are not this simple. And in many cases, some of the problems don't admit an obvious recursive decomposition until you come up with one. So it turns out this iterative algorithm actually evaluates subproblems according to that topologically sorted ordering. And that's why it doesn't have the duplication. It is actually performing, in a sense, the same recursive computation that we were doing with the recursive algorithm, but it's doing it more efficiently because of the way it structures the order of execution of subproblems. And as I observed earlier, it turns out that the correct order of execution, so the order in which to do the subproblems efficiently, is pretty obvious. I just do f of 0, then f of 1, then f of 2, and so on. I go up in numerical order. Although it's sort of obvious, actually establishing that isn't necessarily easy, and using that graph model helps me to do it. So the process of taking a problem, modeling the subproblems, and then coming up with a model of those subproblems that allows them to be evaluated efficiently, and then designing an algorithm based on that evaluation order, that is an example of an optimization technique, which we call dynamic programming. So the term dynamic programming isn't what the algorithm does, it's how we create the algorithm. It's a technique we use to design the algorithm. As I mentioned earlier, whereas last time, for example, Jarnick's algorithm is an algorithm that performs optimization to solve a problem, the algorithm I just came up with was designed as a result of optimization. So the optimization we're doing in this lecture is optimization of algorithms, not optimization of solutions. Although it turns out, as we'll see, we often use dynamic programming to create algorithms that solve other optimization problems. Okay, so where does that leave us? The main outcome of this lecture, and if you really don't want the history lesson you're about to get, then you can skip over it, I suppose, but the main outcome of this lecture is to talk about a few problems and ways to use dynamic programming to create efficient algorithms for those problems. Before we can do that, I think it's actually really important that I talk about what the term dynamic programming means. And because I said earlier, it's a bit of a made-up term, I at least want to come up with a definition that we can agree on for this course for the purposes of designing algorithms. And so, long tangent incoming, but you can't stop me, I'm going to do it. I want to talk about, first off, what does the word programming mean here? Because that's a bit of an unknown. I mentioned it doesn't mean computer programming. Okay, wait a minute. Why do we call it computer programming? What does the word program actually mean? I'm going to start there. So dynamic programming can be applied to a variety of problems. In general, whenever you see that overlapping subproblem situation in a recursive decomposition, that's a sign that dynamic programming might help you. But before we get to that, I want to talk about what dynamic programming actually means. So what does the phrase dynamic programming actually mean? I'm going to start with this word programming. Here is a photo of a computer called Colossus Mark II. It was one of several computers called Colossus that were developed during the Second World War to assist in the code-breaking efforts. This was in the UK that this was happening. And a lot of huge developments in historical computer science, a lot of massive steps forward in the development of computing machines happened as part of the code-breaking effort in World War II. The Colossus Mark II was developed to assist with breaking the Lorentz cipher. Now, one interesting aspect of the Colossus computers was that unlike most previous computation devices, not all of them, but most of them, the sequence of calculations the computer would perform wasn't fixed. So the idea of having an electrical or electronic or electromechanical device that performed computations, that wasn't new at the time. So that is, it was possible, and it had already been done, to build a device, a purpose-built device to perform a specific calculation. What was unique about Colossus was that it had a bunch of computational units that could be rearranged in a sense. You could connect them together in different orders to perform different calculations. It was configurable, which was something that was relatively new. It wasn't the first one to have this property. So there were previous primordial computers that had some level of configurability, but they may not have been known to the people working in the Allied code-breaking effort for a variety of different reasons, or it wouldn't have been understood until later to what extent they could be configured. There's some really interesting history there of basically the question that has been studied for a long time of what was the first programmable computer? And the answer sort of surprised people because it turns out there was a computer from much earlier than this, from I think the late 1930s, that turned out to be programmable by the modern standard, to be what we call Turing complete. That name Turing is in there. It's interesting because Turing is a name that comes out of the UK code-breaking effort in World War II. But anyway, from the standards of the time, one unique thing about Colossus was that the sequence of calculations wasn't fixed in advance, and therefore the device could be reconfigured to perform different tasks. And the way this would work is, it wasn't like you could pull up a text editor or something. Instead, you could use panels of switches and different patch cables and rewire the machine, so reconnect the order in which computation units were connected to each other to reconfigure the path of data, and that means you're changing the set of operations performed to produce the final result. Now, at about the same time, in the US, a computer called ENIAC was being developed, and it stands for this thing, so that's a nice, crunchy acronym, I guess. And unlike Colossus, ENIAC was actually designed to be modular and flexible, so it was designed so that to deliberately allow that reconfiguration. So the Colossus machines could be reconfigured, but still they were designed for pretty much code breaking. The reconfigurability was sort of an incidental thing, whereas ENIAC was deliberately designed for that reconfigurability, even though originally it was intended for one particular use, which was calculating tables of artillery trajectories, one of many early computational tasks that was really beneficial to automate. But the idea was ENIAC was designed with this thought that it might be reconfigured later for use by other computations. It was designed deliberately to be modular and flexible, and it took years to create it. And while it was being created, it came to the attention of this guy. So here he is again, John von Neumann. And as it happens, I've mentioned this already back in, I guess, lecture 9 or something. By the time ENIAC was actually finished, so by the time it was ready for use, von Neumann had found out about it, and von Neumann was involved in a lot of things, but one of the things he was involved with at the time was the Manhattan Project, the development of the atomic bomb. And when it came to his attention that they were building this reconfigurable computer, he somehow wormed his way into the development of ENIAC, and by the time that ENIAC was ready, he had basically co-opted it for use by the Manhattan Project. And so it had been co-opted for calculations related to atomic weapons, although as I recall, I think that by the time they actually used it, they had already tested the first atomic bomb or something. The simulations they used ENIAC for were for other future tests after that. And so John von Neumann somehow managed to co-opt it, and I mean, I guess it's sort of hard to say no to him because he was such a influential figure in that field, and I'm sure he had a powerful enough personality given his expertise in pretty much every area relevant to computation at the time. I've mentioned mentioned before that, well, we in computer science like to say, wow, John von Neumann was a pretty big deal as a computer scientist. The problem is when you claim von Neumann as a computer scientist, the mathematicians show up out of nowhere and say, hey, wait a minute, von Neumann was actually a mathematician that dabbled in computer science. And as soon as they hear this, the physicists jump into the room and say, wait a minute, von Neumann was actually a physicist that dabbled in math and computer science. And then out of nowhere, the economists show up and they're like, hey, wait a minute, von Neumann was actually an economist because he made massive contributions in economics as well. Von Neumann was actually an economist that happened to, as a hobby, do some physics, math, and statistics and computer science. Okay, whatever. So von Neumann was a pretty big deal. And it is due to him that the first computer that could be reconfigured, the ENIAC, had its first reconfiguration and what we would now call its first programs written. That said, at the time, the idea of configuring processing units for a particular algorithm, so that is, you have this computational device that can be reconfigured. Here's a whole bunch of patch cables sitting in that photo right there. Suppose you have this computational device that can be reconfigured. The process of configuring it to perform a particular task was sort of considered to be a type of scheduling task. That's interesting. Earlier in this lecture, I suddenly observed that something else was a sort of scheduling task. And this makes some amount of sense. So they didn't have a word for the process of configuring a computer to do a certain thing back then. And I guess it makes sense. You could view an algorithm as a schedule for operations to perform on data. That is, if I write some pseudocode here, like, x gets y plus 1 and z gets x squared plus y or whatever, well, I guess you could argue that what's really happening, I'm performing these operations one after another, is I'm scheduling a sequence of manipulations on some data. And so I suppose it makes sense when it came time to coin a term to refer to the process of telling a computer what to do, of configuring the operations of a computer to perform some algorithm, you could think of that as a sort of scheduling task. And the question was, what is the word that we should use for the process of telling a computer what to do? And if we think of it as a scheduling task, why not go and find a word that refers to a schedule? And that brings us to the English word program. So the English word program has been around for hundreds of years. It is not a word that we invented just for computers. The English word program, broadly speaking, sort of means a concrete plan or a schedule of events. Examples of the English word program might be, suppose you decided to go to the symphony in 1947, or even in the present day, you might receive at the door a program that tells you what you would be hearing that evening. And if you take a course in algorithms, which is probably the reason you're listening to this right now, then likely the reason is because you are in an academic program. And if you turn on the TV, which I don't think people do anymore, frankly, but back in the 90s, if you turn on the TV on Thursday night or something, then you might watch a television program. And we use the term, let's say, television program or TV show or whatever to refer to a specific, like these days we watch shows on streaming services. When I say I'm going to go watch a TV show or I'm going to go watch a TV program, what I mean is I'm going to watch a 20-minute or 45-minute video stream. But the term TV program, the term to refer to a TV show, like an hour of television, the reason we call that a television program was that, when television first came into existence, we had to develop a schedule of who would have the air at a particular time of day. So a particular hour of a particular evening of the week might be dedicated to a particular thing, and we would call that programming, the task of coming up with a schedule of events for television. And so calling something a television program is just a relic of that use of the term. So the English word program basically just refers to a sort of schedule or a plan of events. And it made sense if we thought of the process of telling a computer what to do as a scheduling task, that the process of telling it what to do might be called computer programming. So by the end of the Second World War, the process of planning computations came to be known as programming a computer. Now, before that time, the word programming wasn't used. It didn't really reach widespread use until maybe 1945 or so. And so until that happened in 1945, the scientists who did the programming were typically called operators instead of programmers. And that made some sense because if we view the computer as a machine, well, then somebody who uses the machine is an operator. I also want to observe, though, that there is there's an interesting sort of, I don't know, sociological aspect to this, which is that the word operator does, by modern standards, sound quite a bit more pedestrian than the word programmer. And there's a certain aspect, a certain sort of nasty bit of, I don't know, like classism behind that to a certain extent. That is, we have come to associate in English the word programmer as applied to computers with a certain level of, let's say, education or a certain occupation with a certain status, whereas the word operator, as in somebody who uses a machine, has taken on a different meaning. And a lot of that is basically just cultural. That is, the word operator could reasonably apply to somebody operating a machine that requires a PhD to operate. Not that, and I should be clear about this, not that necessarily having a PhD makes you any better qualified at anything, just to be clear about that. But until the term programmer was coined, it made sense to call the people that were actually doing the programming, to call them operators instead. Now, I've now explained what the word programming means, I guess, and I want to come back to that in a minute, but since I've been talking about these historical computers, I do have to bring something else up. It's really important that we as computer scientists understand the history of computing for a lot of reasons. That is, a lot of the things that we have to deal with today in computing, like definitions and stuff, stem from historical things that happened 80 or 100 years ago that don't necessarily make sense in a modern context. That is, the word programming is a bit of a strange anachronism because we associate it with writing code, but it was coined in the context of scheduling. And a lot of definitions that we've seen in this course also don't seem to make very much sense anymore because the context in which they were created no longer exists. The same way that like the save icon in programs up until recently was typically like an old-fashioned so-called floppy disk, which people don't have anymore and they haven't had in like 25 or 30 years. So what I want to observe is there's a bit of a dark side of that history of computing, which is that we know a lot about the history of computing basically because there are certain things that did get documented and certain things that didn't. It's pretty common if you open a book about computer science, about some introductory book about computer science, to see things like discussions of the ENIAC or Colossus computers. But we have to understand that, as with any other historical record, the things that we tend to learn about are a function of what people chose to document, which is also, in turn, a function of what people thought was important and what people thought wasn't important. So one thing we should observe, we've been looking at these photos of old computers for the last few minutes, is that because of the way the wartime economy worked, the vast majority of the scientists programming the Colossus and ENIAC machines were women. And due to the pervasive sexism at the time, they weren't given any credit. And that actually persists to this day. And you know I made a big deal about who should get credit for the name of an algorithm in the last lecture, so I'm not going to pass up the opportunity to make a big deal about this as well. And so one thing we should observe, and so if you read about the way that the wartime economy worked, what you might learn as well, what you might already know, is that on the so-called home front, a lot of the jobs were held by women who were summarily dismissed pretty much when the war ended. And I guess you could say then the men came home from war. And that's a bit of a travesty in itself. So highly qualified people found themselves out of a job for reasons that had nothing to do with their qualifications. And the majority of the scientists that engaged in programming, although at the time they might have been called operators, these were people that had master's degrees or PhDs in mathematics. They were women and they didn't get any credit. That is, at the end of the day, when somebody was given credit for this project of designing this computer and programming it, it generally was the management who were men, whether they did any of the programming or not. And typically it turned out that they didn't. It turned out that they were typical management that basically sat around signing off on things and taking credit for things. And that means that even as of 2025, it actually isn't clear when we look at these historical photos who it is that's in them, because the photographer took these photos and then, later the photos are published with all sorts of captions that would, label the technical components being depicted, but wouldn't give the names of the human beings in the photo, which is already a bit weird because if you go and look at other documentation of industrial machinery, where you might see a man wearing a suit and a fedora standing next to a large industrial machine, you will generally notice that that person is named in the caption of the photo. So that is, the photographer or whoever was documenting it did think that it would make sense to take down the name of the man in the photo, but nobody bothered to take down the names of the women who were operating and programming these machines, some of the pioneers of computer programming. They didn't actually get any recognition. And that means that our ability to identify the people in this photo basically is something that's had to happen retroactively. So we do now know know the two people in this photo of the ENIAC are Jean Bartik and Francis Spence. And after a great deal, apparently quite a search, it was determined that the two programmers depicted in this photograph of the Colossus are Dorothy Dubuisson and Elsie Booker. And just to be clear, it was known at the time, the identities of all the people working at the facility. So that is, they did keep records of who worked with these computers. The issue is that when you look at a particular photo of the computer and there are people in it, you then have to, I guess by process of elimination, work backwards and figure out which of the employees of the facility were standing in frame at the time. And it is a bit ridiculous for that they couldn't bother to take that information down because they documented pretty much everything else meticulously. There's something extremely sort of creepy about that whole business. And I'm afraid that the problematic nature of the way that computer science treated many of its early pioneers doesn't end there. So the fact that contributions of pioneering women in computer science were basically erased or pretty much ignored for, in some cases, decades after the fact is a pretty big issue, frankly. Like that's a bit of a travesty. The other people that worked on these pioneering computers didn't get very much, they had a pretty rough time of it as well. So one person who you probably do already know about because culture has found a way of over time trying to, in hindsight, apologize to him is Alan Turing. I mentioned earlier the idea that there was an early computer that is what's known as Turing complete. That is, Alan Turing was so influential in the development of computer science that there are many really fundamental concepts, such as what does it mean for a computer to be able to compute things that are actually named after Alan Turing. And he was treated the way I want to describe the way he was treated is not something I'd like to commit to video, I guess. Come to the office hours and I'll give you an unblemished account of what I feel about the way he was treated. It was pretty terribly. He did a lot of things. He made a lot of contributions that were instrumental in the success of the war effort, and he was not given any credit at the time because his contributions were classified. And then the UK government, which would have known about the weight of his contributions, treated him absolutely terribly for reasons that had nothing to do with anything related to his qualifications and, in a sense, completely diminished the contributions he'd made. One of the reasons why we as computer scientists now have to be careful to try and correct these historical wrongs, to be aware of them and do whatever we can to prevent them from happening again, is because if the contributions of pioneers like this are diminished, then we are, as a discipline, sort of eliminating one avenue to make further progress. People that the early computer programmers, pioneers like the women in this photograph, that were programmers and were performing a task that's far harder than any of the programming that I've ever done. That is, the people in this photograph didn't have the option of opening up a text editor to write some code and running it through a compiler that would give them, to some extent, helpful errors that helped them fix things. They were plugging different patch cables in on a plug board and still being able to implement algorithms. They didn't have all the processing power that I have today. They didn't have all of the computer memory that I have today, and yet they were able to program the computers. Their jobs were far harder than my job is now. By erasing their contributions, we might have missed out on tons of other fundamental contributions to our discipline, and that's a huge deal. We can't afford to miss out on those things. And so it's up to all of us to try and prevent that from happening again. And also up to all of us to try and ensure that when this sort of thing has happened, when these travesties have occurred, people not being given recognition for their contributions, that we do whatever we can to try and fix that in hindsight. So at least now we know the names of these people. Anyway, so okay, there's that tangent. And then to bring our history lesson to a close, today the term programming has become synonymous with computer programming, especially in a course like this. If I say the word programming, obviously we think about writing code. However, the word program has a history that goes back far beyond computer programming, and in particular in mathematics, it turns out that the word programming was often used to describe optimization problems. And remember that mathematical optimization can occur outside of the realm of computer science. One form of optimization that you might have seen already is in a calculus course. If you saw a function like, here's f of x equals, 5x squared plus 6x plus 10, could you find me the value of x that results in the global minimum of f of x, if it exists? So could you find me the minimum value that f of x ever takes on? And you might recall that one way you can do that is by computing the derivative and setting it to 0. That's an example of an optimization problem. Find the minimum of a function, or find the maximum of a function. I don't think f of x here has a maximum value. So an example of a mathematical optimization problem is what's called a linear program. And a linear program is an optimization problem that takes some linear function on some number of variables. And linear programming people would probably laugh at this function here because it only has two variables. And that's typically considered a rather easy linear optimization problem. But suppose I have this function 2x minus 5y. That is a linear function of two variables. I want to find the maximum value of that function subject to this sequence of constraints. So x minus y must be less than or equal to 10. 2x plus 3y must be greater than or equal to 6, x plus y must be less than or equal to 17, and x must be greater than or equal to 0. Notice that all of the functions on either side of the inequality signs are linear functions. The study of optimizing linear functions, like 2x minus 5y, subject to linear constraints, that is called linear programming. And this style of optimization problem is called a linear program. And the reason for that is because, again, optimization problems often arose in practice as something that was viewed as akin to a scheduling or organizational problem. And we'll actually see examples of this later. So the purpose of this lecture is not to talk about linear programming as much as I might want to, but it turns out that later in the course, we are going to see some algorithms applied to graphs. So here's an interesting looking graph. I can't wait to find out what this is all about. Some of the algorithms that we study later turn out to be applications of linear programming. They turn out to be, in a sense, special cases of linear programs. And the study of linear programming, depending on which university you look at, could be something that the math department covers or the computer science department covers. But there are entire courses about linear programming applications and algorithms that are offered in computer science. I know this because I teach one of them. In this university, there is a fourth year and graduate level course on linear programming that covers the theory, applications, and algorithms to solve linear programs. Because that's a big deal in computer science. And it also, like many other optimization techniques, plays into a lot of areas that have reached prominence in the last few years, so things like machine learning and artificial intelligence. The process of optimizing, so if instead of thinking about a linear function with linear constraints, if instead the thing that we are optimizing is a multi-stage decision process, for example, such as finding the best way to evaluate a sequence of subproblems, so that is the modeling that we did earlier, that is called dynamic programming. And we think here of the word programming as meaning optimization. So think of it like dynamic optimization. Don't think the word programming means computer programming. And that's the key clarification. And I realize that my tangent has now taken about 25 minutes, but I stand by it. And you could have skipped over it. Remember, this is a video. So the key clarification for this point of my tangent is dynamic programming is an optimization technique. That's all it is. It has nothing inherently to do with computer programming. In an algorithms course like this one, we use dynamic programming to create algorithms because we are obsessed with algorithms. But there are tons of other applications of dynamic programming that have nothing to do with developing algorithms. It's true that we often use for all sorts of optimization problems computational assistance, but that doesn't mean the optimization problem itself is inherently computational. So we are going to use dynamic programming techniques, not all of them, because dynamic programming is a bit of an expansive thing. We're going to use dynamic programming techniques to derive efficient algorithms for certain types of algorithmic problems. Now, wait a minute. Did I actually answer the question? And the answer is probably no. I just spent a bunch of time talking about what the word programming meant and showing pictures of old computers. And, of course, talking about some social problems that we need to do our best as people in this discipline to try and, over time, ameliorate. Okay, great, but I never actually defined dynamic programming. Let's try that again. Okay, so the inventor of the term dynamic programming, the originator of that term, is generally considered, so is recognized to be a mathematician named Richard Bellman, who was a pretty influential guy. He made lots of contributions to our field, to applied math, and even to fields like biology. Actually, I think he founded a major journal in bioinformatics or something. So Bellman began using this term dynamic programming sometime in like the early 1950s, maybe. Richard Bellman worked at a place called the Rand Corporation. So he was a researcher, but he didn't work directly in academia at the time. He worked at the Rand Corporation, which was a sort of quasi-private, quasi-public corporation that did a lot of research that was sponsored by the U.S. government and the U.S. military. We're going to see an algorithm that Bellman created in a couple of lectures called the Bellman-Ford algorithm, where both Bellman and Ford worked at the Rand Corporation, and I'll talk more about the Rand Corporation then. And so Bellman invented this term dynamic programming to refer to various optimization things that he was doing. And I mentioned at the beginning that nobody can quite understand, nobody can quite clarify what the term means, and that is because it doesn't doesn't seem like it originally had any specific definition. So Bellman, in his autobiography that was published in the 1980s, claimed that basically he had made up the term dynamic programming because it sounded cool. So to summarize his story, he had to meet with the U.S. Secretary of Defense because the research he was doing at the RAND Corporation was largely funded by the U.S. government, by the U.S. military in particular, I think maybe by the Air Force. And he felt like the U.S. Secretary of Defense had absolutely no patience for the idea of people doing math research. He felt that like the Secretary of Defense thought that was stupid and that it had no real concrete relevance. And so Bellman figured that if he told the Secretary of Defense that he was doing mathematical research, he wouldn't get any funding. And so he wanted to make up a term for what he was doing that, sounded like the kind of thing the military would want to get involved with. And he noticed that a lot of people were talking about the word programming to refer to optimization problems, for example, linear programming at the time, and that a lot of people were throwing around the word dynamic because, dynamic sort of sounds cool. It sort of sounds like you're solving something serious. And so he decided to call his work dynamic programming because he felt like this would appeal to the Secretary of Defense. Okay, that's Bellman's story. Now, Bellman's colleagues at the RAND Corporation pointed out that they didn't really believe this. One of the reasons was that Bellman referred to a specific guy that was the Secretary of Defense, and yet his colleagues remember that he was using the word dynamic programming even before that Secretary of Defense was in office. So that's a bit peculiar. Additionally, one of Bellman's other colleagues claimed that Bellman had told him that Bellman had just made up the term dynamic programming because one of their other colleagues named Danzig, George Danzig, who is a famous pioneer of the field of linear programming. I should also add that one of the other pioneers of the field of linear programming was in fact John von Neumann, because no story about computer science in the 1950s is complete without John von Neumann. And so Danzig, which was Bellman's colleague at the RAND Corporation, had been working on algorithms to do with linear programming, and he was kind of a big deal in that field, and linear programming was kind of a big deal as well. And so Bellman apparently just wanted to upstage Danzig, and so Bellman then decided to call his thing dynamic programming, which sounds even more exciting than, plain old linear programming. Okay, so what this means is that Bellman had apparently told two different stories about where he got the term dynamic programming. Neither of those two stories involves the term being made up for any, practical reason, like based on any concrete definition or mathematical definition. Instead, both of the stories that Bellman told involved the word dynamic programming being invented because it, sort of sounded cool. And that was it. Maybe because he wanted to get funding for his research, which I guess I can sympathize with. Sometimes you do need to do a little bit of PR for things like that. So Bellman later wrote a book about dynamic programming, and I took a look at it. It is a bit of a dry read, I guess, to be diplomatic. And so the fact that Bellman had to sort of, in his book, come up with a definition for it, maybe sort of reverse engineer a definition, I guess that can explain why modern sources don't quite know what dynamic programming means. They can't agree on a common definition. So in this course, here's a definition that we are going to use. We're going to use dynamic programming as an algorithm design technique. It's something that we use to help us create algorithms for a task. And we will typically employ it as follows. I have a task, I have some problem I want to solve. I'm going to find a recursive decomposition of that problem. And in particular, now this paragraph is all stuff that you already know. This is formally defining what a recursive decomposition is. And so don't worry about it too much. It's exactly what you think it is. But to be formal, a recursive decomposition in this context means that I can solve a large instance of the problem by breaking it into smaller instances of the same problem and then combining together the solution of those smaller instances to create a solution to the larger instance. And if there's a way of doing that, if I can turn optimal solutions of small instances into an optimal solution of a larger instance, then the term that's typically used to refer to that situation is that the problem has what's called optimal substructure. And if you open up an algorithms textbook that talks about dynamic programming, I can guarantee you that within a few paragraphs, they will use the term optimal substructure. I don't think we need this term very much in this course because I feel like it is something that applies pretty much naturally to the recursive decompositions that we know and love. Because why are we solving a problem recursively if it doesn't have optimal substructure? But that's where that term comes from, and if you ever hear it, that's what it means. Okay, so I find a recursive decomposition, and then I determine an efficient way to evaluate that recursive decomposition. Now, this applies in two ways, and in my mind, the real dynamic programming is happening in step 2. Some aspects of dynamic programming are finding the recursive decomposition, but for our purposes, because we're already pretty good at that, the dynamic programming itself is how I determine an efficient way to evaluate the subproblems in some order or whatever else. It's not just the ordering of subproblems that's always the issue. It could be other aspects as well. And what we're going to see in the examples I'm going to do in a few minutes is that dynamic programming is a technique that requires some creativity. So it requires us to understand and deconstruct the problem that we're solving. It's not like it's a recipe that we can just apply to any problem. That is, how I apply it to one problem versus another depends on the specific contours of that problem. So step 2 is I determine an efficient way of evaluating the recursive decomposition. Now this could be as simple as finding an ordering of subproblems, but I could also have to do things like if I want to solve a particular complicated problem, I might choose instead to solve an easier version of the same problem and then work backwards from the easy version to find a solution to the harder version. And that also is a bit of dynamic programming. It's a way of optimizing the sequence of decisions that I have to make. And then step 3, which in some cases is almost an afterthought, as we'll see later in this lecture, step 3 is then I create some implementation that allows me to do what to implement what I've created in steps 1 and 2. So, for example, back with the Fibonacci sequence, I spent a lot of time modeling or analyzing and then modeling the subproblems. And once I figured out which subproblems to solve, then I turned it into this iterative algorithm that turned out to be a pretty straightforward iterative algorithm. And I think one hallmark of algorithms generated by dynamic programming is that it often turns out that the implementation is sort of deceptively simple. It's often a couple of nested loops or something. And it almost feels like the problem is obvious at that point. That's because all of the hard work went into finding that simple decomposition or that simple implementation of a recursive decomposition. And so often when you see an algorithm created by dynamic programming, it looks sort of like straightforward, and yet actually coming up with that algorithm can be quite difficult. Now, typically, most sources will claim that dynamic programming is only necessary and only really makes sense if you have these overlapping subproblems. In other words, if your recursive decomposition allows you to have non-overlapping subproblems, so disjoint subproblems, well, then you could just use an ordinary recursive algorithm because then you've got the divide and conquer situation. To be honest, although I agree with this logic, which is that obviously for merge sort, we didn't need to use dynamic programming. We could just do a straightforward recursive decomposition. I don't like the implication that divide and conquer is separate from dynamic programming. Instead, I like to think about divide and conquer decompositions as being a sort of easy special case of dynamic programming. Because finding the decomposition still counts as one of the optimization techniques we're performing with dynamic programming. So I don't like the idea that divide and conquer and dynamic programming are seen as completely separate. Instead, I like to think about divide and conquer as being sort of the easy case of the recursive decomposition that we find with dynamic programming. Okay, so in general, we will find in this course that the algorithms that we create with dynamic programming often require very little code and seem to always involve storing a table of values. And that's interesting, like that's a weird coincidence. I want to be absolutely clear that tables of values are not inherently some property of dynamic programming. It just turns out that a lot of dynamic programming algorithms that we encounter can be optimized by using a table of values. And the reason I think that warning is important is that I have looked at some books, some sources that go so far as to basically say, oh, whenever you're looking at a table of values, that's dynamic programming. Or whenever you're doing dynamic programming, your goal is to find a way of caching previously computed results or storing a table of values. I think that completely misses the point. It is true that all of the dynamic programming derived algorithms we are going to see in this lecture and the next one do exploit a table of values. And I think that's a bizarre coincidence. There is no reason we need a table of values to do dynamic programming, and there are plenty of cases where dynamic programming works better if we don't use a table of values. So be careful about that. Don't let anybody fool you into thinking that dynamic programming equals table of values. It just happens that there are a lot of cases where a table of values helps you out. That's a useful technique in dynamic programming, but not necessarily one that is required. Okay, well, there we go. There is about 40 minutes of me trying to deconstruct this strange term, dynamic programming. So when are we going to design some algorithms in this lecture? We're already an hour and 10 minutes in. It's time to get cracking on doing that. So consider this sequence of coins. Now, I don't know what country makes coins like this, but these coins all have different values. Maybe I'm a coin collector and this is their market value or something. So I've laid out all of these coins in a row. And you are allowed to take some of them if you want. You can take any collection of coins you want as long as you never take two coins that are next to each other. So for example, if you want to, you can take this coin and this coin and this coin. And if you want to, you could take this coin and this coin and this coin and this coin. And if you want to, you could take this one and this one and this one and this one. So you can take any collection of coins you want, but you cannot take two that are next to each other. You can take two that are separated by one coin in the middle, but you can never take two coins that are right next to each other. Those are the rules. And the task is, I want you to figure out the largest value you can get out of coins that you can pick up. So you can pick up any collection of coins as long as no two are next to each other. The question is, what is the highest value you can acquire by doing that? In this example, the highest value happens to have total value 39. Now, for the sake of convenience, I'm going to call this $39, even though I know that typically coins, you don't have coins that are worth $17 or whatever. I'm going to say I've picked up $39 worth of coins. Notice that the selection that I made, they weren't just every second coin. So one naive approach, which I think is worth trying, is if you want to find the highest value, just take every second coin. Take as many coins as you possibly can. We may call that a greedy approach. The idea being, if you can't take two coins in a row, then just take every second coin. Then you're picking up a lot of different coins. Hopefully that means you're getting a high value. It turns out, though, in this case, the highest value collection isn't just every second coin. There are cases where I leave two coins in a row that I don't pick up, because if I wait a little bit longer, if I'm more patient, and I don't take the 3, but instead take the 6, I get a higher value overall. And I've chosen this as my introductory example as a way of showing that the problem isn't quite obvious. It's not like I can just try and pick up as many coins as possible, because some coins obviously are worth more than others. Okay, so the task is, I want to find the highest value collection of coins that I am allowed to take. And the way that we're going to break this problem down is we're going to apply dynamic programming techniques, and one of the things we're going to do right off the bat is instead of trying to actually find the collection of coins itself, I'm going to start by solving a sort of easier problem, which is instead of figuring out which specific coins do I pick up, I'm just going to try and figure out the total value I can gain. I'm not going to worry about the selection that gives me that value. I just want to figure out what is the maximum number of dollars that I can pick up at a time if I don't pick up two coins in a row. Now, before we do any of that, I suggest that you pause the video and brainstorm a brute force algorithm for this problem, because we're going to do some analysis. It's not going to be the hardest thing in the world. We're going to derive a pretty efficient algorithm for this problem. But the problem with this sort of issue, with dealing with tasks like this, is that once you identify a task like the coins in a row problem as being amenable to dynamic programming, you might suffer from writer's block because you just sit staring at the screen because you can't think of a dynamic programming solution. Remember that having a solution is better than not having one. And so that even if you can't think of the clever way of solving a problem, you could always try and solve the problem in the obvious way. So before we get all wrapped up in doing this efficiently, I want you to make sure that you know that you could solve this problem by brute force. And you likely would do it recursively, which is actually sort of good, because if you can write a recursive brute force algorithm for something, you might be able to reuse that recursive decomposition and analyze it and model it using a directed acyclic graph such that you can solve it efficiently. So before we get into the weeds of the dynamic programming solution, just make sure you know some way of solving this problem by brute force, so that on an exam or something else, if you were just asked to find the solution to this, whether or not you use dynamic programming, you know that you already have the tools to solve this problem. Okay, so that said, I'm going to begin by numbering all of my coins. I'm going to number them starting at 0 up to n-1. And the reason is because later I'm going to want to use array indexing, basically. So it was a hard decision to index starting at 0 for this formal problem, but I've chosen to do that. So I have n coins, and I'll number them C0 to Cn-1. And the idea here is that Cn-1 might equal 17 or something. It's just the numerical value of that coin. And they are in a sequence, and that makes sense because the ordering of coins is significant, since I can only pick up a coin if it's not next to something I also picked up. So the fact that I can only pick up C1 if I don't pick up C0 and C2 means that the ordering of coins is relevant to this problem. I'm also going to define a function v. And the function vi is the maximum value I can obtain by picking up coins between C0 and Ci inclusive. So up to and including Ci, what is the maximum value I can get? Of course, I have to follow the rules. I can't pick up 2 coins in a row, but vi is the maximum value I can pick up using only those coins. Now, what I said earlier is that we're actually going to begin by solving a sort of simpler problem. The problem I really want to solve is I want you to tell me which coins to pick up. But the problem I'm going to solve first is just the problem of finding vi, which is what is the maximum value you can get. I won't actually tell you the coins, I'll just tell you the maximum value you can get from a particular collection of coins. One hallmark of dynamic programming that we're going to see applies to all of the examples that we do is that usually if you can solve the easier problem of just finding the maximum value or finding whether a solution exists, and you use that information for all possible combinations, you can usually work backwards to find the sequence, the values that you need to achieve that maximum thing. So in this case, if I know the maximum value for all possible values of I, we're going to see that I can reverse engineer the set of coins using that information. I don't need to compute the coins separately. I can just use vi to reverse engineer the set of coins I want. Okay, so I'm actually going to draw this out using this diagram instead. Suppose that I want to know V0. So V0 is what is the maximum value I can get if I'm only allowed to pick up coins from C0 to C0. Okay, well obviously in that case, I can just pick up C0. That's my only choice. So V0 equals C0. Notice that what I'm really doing here is sort of trying to create base cases. I'm actually trying to create some way of recursively, of characterizing VI recursively. Okay, so V0 is C0. What about V1? V1 is the maximum value I can obtain by picking up only coins C0 or C1. Well, I can't pick up both of them because that would break the rules. So I guess if C1 is larger, so if C1 is 1,000 and C0 is 1, well then I want to pick up C1. But if C0 is larger, then I want to pick up C0. So I guess the maximum value I can get from coins C0 and C1 is the maximum of C0 and C1. Okay, so those are 2 base cases. And then I want to illustrate that there is a way of breaking down all the remaining cases recursively. Okay, so V0 equals C0, because obviously if I can pick up only coins C0, then I will. I'll just pick up C0 and I get the value C0. V1, well, I can't pick up both C0 and C1, so either I pick up C0 or I pick up C1, and the one I choose to pick up will always be the one that's worth the most. So V1 is max of C0 and C1. And then for I greater than or equal to 2, so if I want V2 or if I want V3, it turns out I can compute VI recursively. And the way I'm going to choose to do this, there are lots of ways of breaking this down. And in the next few examples, this lecture and the next, a common question that might come to your head is, why is it that I keep choosing to do the recursive case sort of from right to left, as you'll see in a minute? Why don't I start from the left and work to the right? And I actually could do that. It just seems like the algorithm I want works out to be more convenient for me if I go from right to left. In other words, I'm using knowledge that you don't yet have, something that I already know what algorithm I want, and I'm choosing to break it down in a way that's more convenient to me. So for I greater than or equal to 2, I can compute VI recursively, and I can sketch briefly how I do that before I go forward in the slides. So suppose I want VI. So VI would be the maximum value, okay, that's a pretty weird drawing, the maximum value I can obtain from coins C0 through Ci. There are pretty much 2 cases. Either I pick up coin Ci or I don't. So either coin Ci is out or coin Ci is in. If coin Ci is in, then coin Ci minus 1 must be out because I can't pick up 2 coins in a row, which means the maximum value I can get, so the value of Vi in this case would be, well, I chose Ci, and then I'm obviously going to pick up as high value I can out of the remaining coins, which would be everything up to I minus 2. So if Ci is chosen, then Vi is going to be equal to Ci plus V of I minus 2, because obviously Ci minus 1 is out. Ci minus 1 cannot be chosen if Ci is chosen. Now that's one recursive case. The other recursive case, and there are only 2 of them because Ci is either out or it's in, the other recursive case is, what if Ci is out? Well, if Ci is out, then C minus 1 might be in. Maybe not. We don't know yet. But we know that Ci minus 1 could be in. So what happens there is if Ci is not chosen, then basically the highest value I can obtain, because ci is not chosen, is just going to be equal to v of I minus 1. That's it. I just go get the highest value I can out of all the remaining coins, all the coins up to and including vi minus 1. So there's my recursive breakdown. And the idea basically is that if I look only at ci, if I sort of pivot based on that, either ci is in or ci is out. They're just two cases. I just have to work out the recursive decomposition for both cases. Okay, I'll let the slides catch up. So if ci is chosen, then ci minus 1 cannot be chosen. So the maximum possible value is v of I minus 2 all plus ci. If ci is excluded, well then I don't know what the status of any of the other coins is. Ci minus 1 might be in and it might be out. We don't know. We don't want to try and figure that out because we can just say, well look, the maximum value I can get from all this stuff is a v of I minus 1. And ci can never be chosen if I've decided it's excluded, and so the maximum value achievable in this case is v of I minus 1. And so I think I now have a recursive decomposition. So in the recursive case, vi will just be the maximum of those two cases. I mean, so either ci is in or ci is out. Well, which one is it? Well, it'll be the one that results in the better value. If excluding ci gets me a better value than including it, then I'll exclude it. So that means the recursive case is vi is the maximum of the two recursive cases, the one where ci is in and the one where ci is out. So these are mutually exclusive cases, although they do overlap. So, and it's important to indicate that those two terms can coexist. The reason why these two cases are mutually exclusive is that either ci is in or ci is out. Here's the case where it's in, here's the case where it's out. Clearly, those are exclusive cases because if ci is in, it can't also be out. And if ci is out, it can't also be in. So the two cases are mutually exclusive and they cover all possibilities. Ci has to be either in or out. But the recursive calls themselves might overlap. And the reason for that is maybe it's sort of obvious. So the recursive calls for vi are to v of I minus 2 and to v of I minus 1. But let's look at the recursive case for vi minus 1. So that's going to equal max of v of I minus 3 plus c of I minus 1 or v of I minus 2. So I've just taken the recursive case and I've rewritten it for I minus 1. Notice that the two recursive calls I do for I are I minus 2 and I minus 1. But when I do the recursive call for I minus 1, I see another recursive call for I minus 2. And in fact, if I look inside the recursive call for I minus 2, there will be a recursive call to I minus 3. So although my two recursive cases are exclusive, that doesn't mean that they don't perform the same computations internally, that they don't share certain subproblems. And so what I notice is that I do seem to have those overlapping subproblems where applying a dynamic optimization technique might help me. So here's my completed recursive form for vi. So if I is equal to 0, it's just c0. If I is equal to 1, it's the max of c0 and c1. And otherwise, the general recursive case, it is the maximum of v of I minus 2 plus ci. That's the case where ci is in. And v of I minus 1, which is the case where ci is out. Okay, now the question is, how can I evaluate this efficiently? So clearly, I've written a recurrence. I could easily write a recursive function that evaluates the recurrence directly. I could just do a recursive call to compute this. However, if you try doing such a thing, you would observe that it's exponential time. So that is, try doing it for a collection of 20 coins and get back to me when it finishes. It's going to take a little while. And that's basically because it turns out that the recursive pattern here, if you stare at it, it's pretty obvious the recursive pattern is very similar to the Fibonacci sequence. I've got two base cases, and then every subsequent case does two recursive calls into I minus 2 and I minus 1. And so maybe it doesn't surprise us that this is going to suffer from the same exponential time explosion that I got with the Fibonacci sequence. In fact, my analysis is going to be pretty much the same. If I work out the graph of dependencies as a directed acyclic graph, it is in fact the exact same one as the Fibonacci sequence. And so I can apply the same technique. Similar to my Fibonacci sequence, I could evaluate an arbitrary value of vi. So for example, if I want v5, I work out this dependency graph, and then I go through each of the vertices in a topologically sorted ordering, such that when I need to compute v4, if I want the values of v2 and v3, I just go back and I look at the value I stored in v2 and the value I stored in v3, and I use those. I don't fully recompute them recursively, I just keep them around, and I can compute them in this pretty sort of obvious numerical order to get each value before any of its dependents are evaluated. Anything that depends upon it is needed. And so, unsurprisingly, I could basically take that iterative Fibonacci algorithm and adapt it to the case of solving the coins in a row problem. So this pseudocode computes in linear time the value of Vn. You give me the coins, C0 through Cn, and it computes the result in linear time using pretty much the same logic as my iterative Fibonacci algorithm. And that's why, an hour ago, I wanted to explain why my iterative Fibonacci algorithm was written the way it was. So this adaptation wouldn't be too surprising. Now, another way of doing it, although it's unclear at this point why I might want to do it this way, because if all I want is the value of Vn, I could just call this function to do it, and notice how this function is linear time and constant space. I don't need to allocate any arrays. Another option, though, would be to explicitly store a table of values, so here it comes, a table of values for my function v. And I could do this pretty easily as well. It's really the same difficulty as the previous algorithm, except for the fact that there's fewer if statements because I'm not having to, I'm able to store everything in a table pretty much. So what I do is I create an array of size n plus 1. The reason for the plus 1 there is you'll notice there actually are n plus 1 coins because I've numbered up to Cn. And then I do v0 equals C0, so these are the two base cases. And then I just run a loop to evaluate the recursive case. And it's pretty clear that because I'm always working with previous values of I, so I minus 2, I minus 1, that by the time I'm computing vi, the values of v of I minus 2 and v I minus 1 will be available. So this pseudocode creates a table of values of all of the different values of v. And the question we should ask is, if all I want is to know Vn, why would I bother doing this? And the answer is, it turns out if I use, so suppose I rewrote the algorithm not to return Vn, but just to return the full table V. If I do that, it turns out I can use the numerical values of V to figure out specifically which coins I should choose. Because notice how the problem I've been solving up until this point, computing the value of V, all V tells me is the maximum value I can get from the coins. It doesn't tell me which coins to take. I eventually want to know a specific selection of coins to take. And it turns out that using a table of values for V, I can do that. I don't need to do any other computation to make that happen. And I'll show you how that works. So here's my collection of coins, and I have computed the value of V for each index I. So for example, when I say V3 equals 9, what I mean is that if I'm only allowed to pick up coins from among the first 4 coins, so coin 0 through coin 3, the maximum value I can get is 9. I think that would be if I pick up the 6 and the 3. And if I take a look at, let's say, V5, the fact that that equals 12 means that there is some way of picking up total value 12 from among coin 0 through coin 5. I think here I would probably do that by picking up the 2 6s. That's the easiest way of making that happen. So I have this complete set of values for V, and what I'm going to argue is that it is actually relatively straightforward. It requires a little bit of reverse engineering of the problem, but I will be able to work out a pretty convenient algorithm that lets me work out which coins to take based on the values of V. And the way I'll do this is by taking a look at the recursive case and observing there's a pattern that's going to form if I look at the values of V working my way backwards from the end. So our task is find a valid selection of coins that has total value 39 from this. And the way I do this is I have the values of V, and I look at the recurrence, and I'm able to see a pattern that'll tell me, so if V of 9 equals 39, what coins gave me that collection? Okay, so if I look at the recurrence, I'm going to look at the recursive case and observe that the recursive case, of course, there are two options. Either VI equals the VI minus 2 plus CI, or VI equals VI minus 1. So basically, if VI minus 2 is smaller than VI minus 2 plus CI is smaller than VI, I don't take it. And then I take VI minus 1 instead. And one observation, because of the use of the max function here, is that we know that VI is always greater than or equal to VI minus 1. And then the question is, when is VI definitely going to be greater than VI minus 1? Well, certainly if VI is equal to VI minus 1, that's not going to happen. And that's telling me that if VI is greater than VI minus 1, I must have fallen into this case here. And this is the case where coin CI is in my collection. So I notice that if I just look for cases where VI is greater than VI minus 1, that'll tell me when I added coin CI. I don't actually need to recompute the recurrence to do this. I just use the table of values and look at the relationships between each VI and each VI minus 1. So I notice, for example, that V9 is greater than V8, and that tells me that I must have included coin C9. So that means 17 is in. And since 17 is in, since coin C9 is in, coin C8 is automatically out. I don't even bother with V8 after this because coin C8 has to be excluded. Okay, I work my way back to coin number 7. Notice how V7 is equal to V6. What that tells me, though it's possible that there could actually be multiple ways this happens, but it tells me that that means that if I exclude coin 7, so because it's saying that VI equals VI minus 1, if I exclude coin 7, it's not going to hurt me because I can still get the same value using only coins up to coin 6. So I could just exclude coin 7. Now, maybe I could include coin 7. You could argue that, hey, I get value 22. Why not keep coin 7? And I guess my logic is if I can exclude a coin, I might as well exclude it because I don't know that I care that I have the fewest total coins overall, but it does seem as if it's easier for me to have a smaller collection than a larger one. Since V7 equals V6, it doesn't hurt me to exclude V7 because I can still get a value of 22 out of all the coins that are up to coin 6. So since I can exclude V7 or coin 7, I do. Okay, now I look at coin 6. Okay, so V6 is greater than V5, which means I should include coin 6. Otherwise, I don't get the same value potential. Okay, so I include coin 6. That excludes coin 5 automatically. I look at V4. It is greater than V3, so I include coin 4. Okay, and that excludes coin 3. I look at V2. It is the same as V1, which means nothing. It doesn't hurt me if I exclude V2. Okay, so I exclude V2 or C2, and then I look at V1 and it's greater than V0, so I include C1. Okay, so just going back to my observation from a minute ago where I looked at C7 and C6. So V7 equals 22. Is it possible that I could have included coin 7? Well, maybe, but I don't know. It's possible including coin 7 rules out the case where I get total value 22. But I know definitely that if V7 equals V6, that it doesn't hurt me to exclude coin 7. So it's better to exclude it than to run the risk that including it causes me a problem later. And that's just because since V6 equals 22, if I want total value 22, I still have a path to obtain it without C7. So pseudocode for that process is shown here. So basically the first bit is just computing that table of values for V, and that's clearly linear time in N. And then I just make a list. The list I'm going to return, which is called L, is a list of indices of the coins that I take. And I use this loop to find the indices of coins. I start at coin N and I work my way backwards. And basically what I ask at each step is VI equal to VI minus 1? If the answer is yes, that means I do not have to include coin I, and so therefore I choose to exclude it, so I don't have to worry about reverse engineering the recurrence any further. If I can exclude coin I do. And if I equals 0, then there is no previous coin, so then I also just work backwards and then the loop will end. If VI is greater than VI minus 1, I'll fall into this else, in which case I do keep coin CI. Because if we look back to our example just now, every time where VI was greater than VI minus 1, it's telling me that I do need coin CI to get the high total that I want. And so this puts together my list of indices, and notice how it does it without ever actually using the recurrence. It does it by, because we were able to look at the recurrence and see that pattern, all I need is to use my table of values for V. And as I mentioned earlier, it turns out tables of values can be quite helpful when you're using dynamic programming solutions. That doesn't mean that tables of values are necessary, but they do tend to help in all the cases that we see in this course. And that once I have my table of values, I often don't need recourse to the original recurrence or even the values of the coins themselves. I can use my table of values to get everything I want by reverse engineering. And so it's also, I should observe, there is actually also a way of computing the set of indices in forwards order rather than by working backwards. So in addition to computing my table of values V, I could be computing for every index I the set of indices that go with index I, the indices of the best selection of coins that gives me value VI. I could do that. That's not a good idea in this case because it would require me storing the set of indices for every possible value of I, which could waste a lot of space pretty much. I only need the set of indices that goes with Vn. And therefore, it's better to work backwards from Vn than compute every set of indices for other coins because I might not need that set of indices. But your mileage may vary. That is, there are plenty of cases where not using the reverse engineering approach would get you a result just as quickly as it would to use it. However, I pretty much will always choose the approach that works backwards using my table of values. And that brings us to this. So that's the end of the coins in a row problem. And then we see an old friend. There's our old friend, the scale. And no wonder I kept thinking about subset sum earlier, because here we are. We're back with the subset sum problem. So I give you some integer w. That would be the unknown weight on the left-hand side of the scale. Although recall that I'm actually willing to tell you what w is. So unlike the case where the weight is a mystery, I'll tell you the weight, and I want you to find some way of balancing the scale using a collection of other weights that I give you. Now, although we know that the subset sum problem can be phrased without the scale or without the weights, because that's where my brain goes with it, I'm going to keep talking about the thing that we're making a subset of, the set S of integers, as the set of weights to balance the scale. And I'll call W, for the sake of avoiding ambiguity, I'll call it the goal sum. So recall that the subset sum problem is I give you some value W, a positive integer. I give you a set S of n other positive integers, and your job is to figure out whether I can take some subset of S and come up with a subset B that adds to W. And we, of course, studied this before. And I've mentioned that there is no polynomial time algorithm known for the subset sum problem. So here is the statement of the subset sum problem that doesn't have recourse to the scale. I give you a set of integers. I give you a goal sum W. Your job is to find me a subset that adds to W or to report that no such subset exists. There is no algorithm that is polynomial in terms of n that solves this problem. So there is no n to the fifth algorithm, there's no known n to the fifth algorithm, there's no known n to the 100 algorithm, there's no known n to the 1000 algorithm that solves this. We don't know whether such an algorithm exists. So I'm not saying that one doesn't exist, I'm saying that we don't know of one. And I'm also, in a way, I'm also trying to spoil the fact that nothing that we do in this lecture is going to create one. We do not know of one, I don't know of one, nobody else does at the moment. If one was found, that would be a huge deal. But it could be that one does not exist. It could be that there is no such thing. We have no idea. In a previous lecture, back in lecture 12, we developed an exponential time algorithm to solve this and showed that with the addition of a bunch of heuristics, we can often solve this problem practically, even though it is exponential time. There is no polynomial time solution that anybody knows about, but there are still ways of solving the problem, even if they're computationally expensive. The question is, we know that we can solve this problem recursively. Is there a way that we could analyze the subproblems and apply dynamic programming techniques to solve it faster? And the answer, as it turns out, is a resolute yes. We are going to come up with an algorithm that is really fast for certain cases, although it isn't going to be polynomial in n. So what I want to do first is I'm going to do the same trick I did earlier. So earlier with the coins in a row problem, I didn't begin by tackling the original problem. Instead, what I tackled was the problem of just deciding the maximum value. Once I was able to determine the maximum value I could collect, I worked backwards from that to find the actual set of coins that I wanted. I'm going to do the same thing here. So instead of initially solving the problem of finding the subset, I'm going to begin by just solving the problem of deciding whether a subset exists. I'm going to answer a yes or no question. So you give me a set of positive integers and some goal sum W. I'm going to return true if there is a subset that adds to W and false otherwise. I won't give you the subset. I'll just tell you whether there is a subset that exists. And my hope is that once I solve that problem, I can work backwards to actually find the subset efficiently. Okay, consider these weights and suppose that my goal sum is 24. As I mentioned earlier, because in my head this is all about weights on a scale, I'm going to call the individual elements of S weights. So be prepared for that. I tried to train myself not to say it that way, but I was unsuccessful by the time I started recording this, so we're going to call them weights. Suppose my goal sum is 24. Now, we saw in an earlier lecture that there are a few tricks we could use that would help narrow the problem down, but we're not going to worry about that now. So it's true, for example, that if my goal sum is 24, I could just ignore the weights 92 and 53 and 58. That would still help me here to some extent. I'm going to ignore that because I just want to describe the algorithm in an abstract sense. And so the observation I want to make is, let's look at the last weight in the sequence. So my goal is to find some recursive decomposition. I could do this by working from the beginning to the end, but I'm going to work from the end backwards for pretty much similar reasons to why I did in the coins in a row problem. So let's look at the weight 7. So I want a subset that adds to, in total, I want it to add to W equals 24. Now, suppose I consider the status of the weight 7. And we know that either 7 is in or 7 is out. In the event that 7 is in, well, then what I really want is a subset of everything else that adds up to 24 minus 7. I want a subset that adds to 17. And so we can see that there is a sort of natural recursion in that, because now what I need to do is find a subset of this smaller collection of weights with this smaller sum. Now, in the event that 7 is excluded, because 7 is either in or it's out, then what I'm looking for is a collection of these weights that adds to 24, because obviously by excluding 7, 7 does not contribute at all to that sum. So I already have the beginnings of a recursive decomposition. I know that if I look at each weight, it's either in or it's out. And whether a subset exists, well, if there's a subset of the remainder that adds to 24, then of course there's a subset of all of them that adds to 24. If I include 7 and there's a subset of the remainder that adds to 17, well, then there's a subset of everything that adds to 24. So I have the beginnings of my recursive decomposition. So in both cases, finding a subset can be reduced to a subproblem over a smaller collection of weights. Now, to formalize this, I'll have to number some things. So in the problem specification, the S itself is actually a set. It has no inherent ordering. But it makes sense, if we want to view it like something we can break down from right to left, it makes sense to give the weights some kind of ordering. So we're going to assign an arbitrary numbering to the elements of S. We can number it however we want. In practice, this isn't really that important, because usually if you're writing an algorithm to do this, it probably is taking the values in S as like a sequence type or something. So in other words, if I write an algorithm where you give me an array that contains the values of S, well then obviously I'll just use the built-in indexing of the array as my numbering of the elements of S. It's sort of, I get it for free pretty much. But in any event, let's assume that we have a numbering of my elements of S. Okay, so I'm working my way towards formalizing the observations I just made. So suppose I want a subset of all of this stuff that adds to W. Well, if I can find a subset of these things that adds to W prime, which will be equal to W minus S of n minus 1, then what I could do is if I find a subset B prime that has these properties, then I could just take B prime, add S of n minus 1 to it, and now I have a subset that adds to W, because, my B prime added to W minus S of n minus 1. It left a perfect gap to bring in S of n minus 1. So that's my first observation. That's a way of formalizing the recursive observation I made earlier. And then a base case I could observe is, look, if there's only one weight, then, whether or not I have a subset that adds to W, well, that's going to be determined based on whether the weight I have equals W. That is, if you want a subset that has total weight 17 here, well, you're in luck if S0 equals 17, and you are out of luck otherwise. So that's a pretty easy base case. Now, there's one quirk about this I haven't illustrated yet, which is what happens if W is 0, and I'll come to that in a minute. Okay, so the observations I've just made imply that if you give me a subset sum instance with a particular set S and a goal sum W, I can break it up into subproblems with parameters S prime W prime, where S prime is always a proper subset of S, so it has fewer weights. It is a smaller problem, and W prime is less than or equal to W. So it could be that the goal sum doesn't decrease, but in my subproblem, the size of my set of weights does decrease. Okay, so to formalize this, I'm going to start by saying, suppose you give me a set of weights S0 through S of n minus 1. I'm going to invent a Boolean function A of ik, which will be either true or false, and we'll let it be true if there is a subset of S0 through Si, which adds to k. So I've parameterized a sort of general version of the problem. You give me a set S of n weights, and you give me a goal sum W. I'm going to define a function A of ik that enumerates a variety of different possibilities. I want to ask for a subset of S0 through Si, whose sum is k. So if you ask me for A, so in other words, if you give me a value of like S is equal to some, like 3, 6, 9, and 12, if that's your value of S, and W is equal to 16, well then I guess what I want, so here there's 4 of these weights, what I want is A of 3, 16. I want to know whether there is a subset of these 4 weights, S0 through S3, that adds to 16. But I'm defining A for a variety of other cases as well. I could ask whether there's a subset of these 3 weights, so be A2, that adds to 9, or adds to 27, or maybe not 27, but maybe 15 or something. So AIK is true if there's a subset of this limited number of weights, which adds to some value k. Now the solution that I want, the actual problem I want to solve, is A of n minus 1 W. It is, if I'm allowed to use all of the weights, can I achieve my real goal sum W? Okay, so now that I have that formalization, I can actually define the function A. Okay, so I've listed 3 base cases. The third one isn't really necessary, but it's there for convenience to make my recursive case a bit less ugly. Okay, so the first base case is, what if we're working with a subset of size 1? So A0k, if k is greater than 0, and otherwise we fall into base case 2, A0k is true only if S0 equals k. So remember that the first index, the index I, is which weights are you allowed to use. If I'm using I equals 0, then the only weight I'm allowed to use is S0. So the subset exists only if S0 itself equals k. Okay, base case 2, which does come up occasionally. What if I'm asking for a subset with sum 0? So that would be A of anything, comma 0. That's true in all cases, because, here's my set of weights. So 3, 6, 10, 17. Is there a subset of this that adds to 0? The answer is absolutely there is. It's the empty set. So if you ask me for a subset with sum 0, the answer is always yes. And so this base case, where k equals 0, is always true. And then finally, as a convenience, if you ever ask me for, A of 5, comma, negative 20, then the answer to that is obviously false. In general, there's no way you can ever get a subset with negative sum. However, I will allow you to ask that question. So I will define A of ik to be, it will be defined for negative values of k, but it's always false. Now this is actually extraneous. That is, when you evaluate it, you don't need to have this built in, but it does make it easier for us to write a recurrence for this. And it'll be clear why when we see the recursive case. So if I ask for a negative sum, the answer is always no, you can't do that. Okay, so here are the recursive cases, and what I'm going to do, as with the coins in a row problem, is break it down by the status of Si. So if you ask me for A of ik, it's going to break into 2 recursive cases. Either Si is in the subset that adds to k, or Si is not in the subset. In the case where Si is not in the subset, well, then all I'm really doing is trying to make a subset with sum k out of all the weights up to I minus 1. So A of ik is true if A of I minus 1k is true. And that's just the case where a subset of all the other weights up to Si adds to k. Recursive case 2. Suppose Si is in. Well, if Si is in, then A of ik is true if A of I minus 1. So if I can use all the other weights to make a subset with total weight, a total sum k minus Si. If I can make a subset with that sum, then I just add Si to that, and I get a subset with sum k. So those are my 2 recursive cases. Si is in or Si is out. And so my recurrence now looks like this. I have to consider both recursive cases, of course, and so I merge them together. Okay, so A of ik is false if k is negative, because you can't have a negative sum in any case. If k is 0, it's always true. If k is greater than 0 and I is equal to 0, then A of ik is true only if S0 itself equals k. And that's the third one of our base cases. And then our recursive case is this. Now, this thing here is the logical OR operator. That's the most mathematical, distinguished looking way of writing logical OR. We're not doing any weird vertical bars here. We're doing this weird symbol that only is used for this purpose. And because aik is a Boolean function, that's why we're using logical OR. So if you can make a subset by excluding si, or if you can make a subset by including si, well, in either case, you're good. And so aik is the logical OR of those 2 subcases. I can take that information and I could use it to map out my graph of subproblems. And for this collection of weights, and actually I should go back and observe this, notice how the collection of subproblems you solve, the recursive structure of the problem, is heavily dependent on the value of the weights you're given and the goal sum. Because the goal sum itself is one of the parameters in the function A, and when I look at my recursive decomposition, the values of the weights, Si, factor into the parameters of the function A, which means the exact graph of subproblems, the exact subproblem decomposition will be different depending on which weights you're given. So suppose I'm given this sequence of weights in this order, 5, 4, 2, 2, and I want W to be equal to 9. Well, then the problem I want to solve is A3, 9. I want to use all the weights up to and including S3 to get the goal sum 9. And then if I look at the recursive decomposition, well, that means that A3, 9, if I go back and apply this recursive case here, A39 is, well, there are 2 options for weight S3. Either it is out, in which case I want to create a subset up to and including S2 that adds to 9, or S3 is in which case I want to create a subset of all the remaining things that adds to 7, because S3 equals 2, so 9 minus 2 equals 7. Okay, and then below that I've got A1, 9, so if I'm trying to solve A2, 9, so S3 is out of the question here, my choice is either that S2 is out, in which case I want to form a subset of size 9 using weights S0 and S1, or S2 is in which case I want to form a subset that adds to 7 using only S0 and S1. So hopefully you can see where I got all of these subproblems in the graph. Notice that from the structure of the graph, it is already clear that I have overlapping subproblems. Because if I look at A17 or A05, they are dependencies of multiple other problems in the graph, which means if I had tried to evaluate A39 with a pure old-fashioned recursive algorithm, in other words, if I just turned this recurrence into a recursive function, then I would see that overlapping compounding recomputation that we saw with the Fibonacci numbers. So this example just by itself is showing us why it's beneficial to try and model our subproblems this way and find a better way to evaluate them. Because if I tried to do it purely recursively, I might see that exponential time explosion that I'm trying to avoid. Okay, next thing I observe is if I look at this graph, and again, the reason that I had the arrows point upwards in the graph is so that topological sorting, as we've defined it earlier in this course, could be applied easily. Notice that if I now want to evaluate A39, if I happen to have the values of A29 and A27 available, it's really easy to do that. So the question is, how do I evaluate my subproblems in an order that allows efficient evaluation? And the answer is in a topologically sorted ordering of the graph. And in this case, although I could run a topological sorting algorithm to find that, I could also just use what I know about the recurrence to observe that there will never be an edge between two things with the same value of I. So there could be an edge between two things with the same value of k, so k equals 9 in both cases. But I can almost break the graph down into levels by the value of I. So there's level 3, or there's the level with I equals 3, the level with I equals 2, the level with I equals 1, and the level with I equals 0. Because the recursive cases always do I minus 1, I know that I'll never have an edge that goes from I equals 1 down to I equals, or sorry, in the opposite, in the wrong direction, or from I equals 1 to equal I equals 1. And so I sort of already know that what I could do is just evaluate everything on the bottom level in whatever order I want, then evaluate everything on the next level up, then the next level after that, then the next level after that. I could just go in ascending order of I. I don't need to run a topological sorting algorithm to make that observation, although having the graph handy does help me with this. Okay, so I want to know the answer. Is there a subset of all of the weights that adds to 9? I want to know whether A39 is true or false. To evaluate this without the compounding recursive duplication, I could just go from the bottom of this graph up. I mean, I keep wanting to call this thing a tree, and I keep wanting to call this thing the root, even though it's not a tree, so it doesn't have a root. So I could evaluate everything on the lowest level. And of course, these are all base cases, so it's pretty easy to do this with the, all of them fall into this case here. And so it's unsurprising that, so S0 itself equals 5. So of course A05 equals true, because I can actually make a subset with total weight 5, total sum 5, by using S0. I can't do that to make a subset of 9 or 7 or 2 or 1. Okay, so on the bottom level A05 is true and everything else is false. I can then work my way up. I can evaluate A19 by just looking at its inbound neighbors and grabbing their truth values and taking the logical OR. And then same thing here, and then the same thing, this one's going to be true. And so I do that, okay? And then I do the same thing for the next level and the next level after that. And sure enough, it turns out that there is, because this is true, a subset of all of the weights that adds to 9. In fact, there could be more than one of them. And we'll see in a minute that it's pretty easy to see from the state of this graph that there is more than one viable subset. Before we go any further, let's just see if we can find the subsets that work. So I think this one definitely works. 5 and 4 add to 9. I think I could also do 5 plus 2 plus 2. So there are at least two different subsets. I think that's it, though. Two different subsets that add to 9 here. And notice that because of the way that we computed these values, so if we go in this topologically sorted ordering, we are able to ensure that by the time I want to compute, let's say A39, the truth values of the things on which it depends will be available. So the computation itself is really simple. I'm just doing a logical OR. I'm just going and grabbing these two values and performing the logical OR operation in a really easy constant time. Okay, so I know that there's a subset that adds to 9. But remember that this idea of solving the true or false problem of does a subset exist wasn't the problem I actually wanted to solve. I wanted to know what the subset was. I want somebody to tell me you need to use weight S0, weight S2, and weight S3, or something like that. I want somebody to tell me the specific indices of the weights in the subset. So the question is, now that I know the truth values of all of the subproblems, can we use that information? Can we work backwards to find a subset? And the answer, it turns out, is yes, very similar to the coin in a row problem. Because I have the graph up, I can actually show how I do this in a graph theoretic way. Really what I want to do is, I can do this either from the bottom up or the top down. I'm going to do it from the top down because it matches up with our algorithm for later better. I actually had slides that I deleted before the lecture started that went from the bottom up, and I felt like that sort of complicates matters unnecessarily. But you could do either. There's no requirement that we do it in the same order I'm doing it here. Basically, if you want a subset, what you could do is start at your original goal, so A39, and then work your way down the graph until you hit a base case, but you're only allowed to walk through nodes that are true. So I could do that with the path I've illustrated here. That brings me all the way down to a base case. And then what I do is I look at the relationships between two neighboring nodes along the path, and I figure out which recursive case that I used. So you'll notice that in this case, A39 recurses into A29. It recurses into a case where the goal sum doesn't change. And we know that the goal sum doesn't change in the event that the weight we're talking about, which would be weight 3, is left out. So that's the kind of deduction I'm doing. It's very similar to the deduction I did in the coins in a row problem. So I could use this path. Now you'll observe that there actually is another path here. So I could also do a path like this one. And it'll be an exercise later to use the same logic I'm going to use to find the subset that corresponds to this path. Okay, so in the event that there are multiple possible paths, that means that there might be multiple subsets, and each of the paths you could take will produce a viable subset. So our goal is to find a path from our original, from the problem that we were actually solving, down through the graph into a base case node, where I'm only allowed to traverse nodes that evaluate to true. And so I can construct a subset. Once I have the path, I can construct the subset either by working my way up from the base case or down from the goal case. Either works. However, I sort of naturally would rather work my way from the bottom up because I like following the path in forwards order. However, I'm going to work backwards from the top because the algorithm we're going to develop later does that, so it's better for consistency. Okay, so the two subproblems on either sides of this edge, A39 and A29, are both true, obviously. And at this point, we'll sort of think of ourselves as standing on this node here and looking at the next thing backwards on the path. So I notice that A29 corresponds to the recursive case where weight S3 was not included, because otherwise I would be working with A27. Okay, so that means S3 is out. So I eliminate S3, it is not in my subset. And then I walk backwards along the path to A29. Okay, if I look at A29, the thing coming before it is actually A19, which is again the case where the weight I'm looking at, that would be weight number 2, S2, is not included because the goal sum doesn't change. Okay, so S2 is excluded as well. Then I look at the node A19. And the thing before it on the path is A05. The goal sum changes. And you can see the reason for that was because this, or I guess not the node, but the edge, corresponds to the recursive case where S1 is in the subset. So, A19 is true because A05, 5 being 9 minus 4, is true. Okay, so that's telling me to put S1 in the subset. And notice how I'm actually able to deduce this without going and looking at the recurrence because I just know that if the goal sum changes, that's because the thing was added. Okay, and then finally I get down to A05, and A05 is a base case. So I have to use the base case logic for that. The reason that A05 is true is because S0 equals 5, which means I can make a subset of total sum 5 by adding S0, so I add S0 to my subset. And notice that now that I'm done, I have actually created a subset with total weight 9. And I did this just by taking my values of the Boolean function a and this lattice that I've created that corresponds to the dependencies of subproblems and working backwards. I didn't need to create some separate algorithm for this. I can just use the truth values that I had and reverse engineer a subset out of those. Now, the exercise that I foreshadowed earlier is, it turns out that there are multiple paths available. So instead of going down the left-hand side, I could have gone down the right-hand side. So a thing you can try doing is employ the same logic I just used to figure out the subset that corresponds to this path here. Okay, now let's look at a different version of the same problem. And I mean, it's pretty much the same problem because the weights are the same. So if we compare this one to the previous slide, the weights that I just went through are 5, 4, 2, 2. The weights I'm going through on this problem are 4, 5, 2, 2. That's the same set of weights. I've just numbered them differently, which of course makes no difference. Like whether a subset exists has no bearing on how I number the weights. And so it shouldn't surprise us that A39 is still true, but it also shouldn't surprise us that even though the set of weights is the same set, because they're in a different number, the decomposition into subproblems looks different. Notice how at this point A05 is false, because of course the first weight is actually 4 at this point. Also notice that instead of there being 2 edges leaving A05, if I look at the bottom layer of my graph, there's only 1 edge leaving each thing. Although I do still have overlapping subproblems because there are 2 different things that depend on A17. And so what I'm illustrating here is that although we had to choose to number our weights as a sort of arbitrary numbering just to break the problem down, the order of that numbering does contribute to the way the problem breaks down into subproblems and therefore does change the lattice that I create. What I'm trying to show here is, unlike the Fibonacci numbers and the coins in a row problem, where we always got this sort of very consistent looking graph of subproblems, here the graph of subproblems is not only sort of unusual looking to begin with, it's pretty wide, it has lots of different vertices with lots of different parameters, but the structure of that graph can change dramatically if I change the weights that I'm working with. And that makes sense because the parameters to the recursive calls are based on the weights that I was given and the order that they're in. So anyway, if I take a look at the path on the left in this graph, notice how there are 2 paths, but they have 2 distinct endpoints on the bottom layer. If I look at the path on the left, okay, well, A39, A29, the goal sum doesn't change, so S3 is out. A29, A19, okay, well, the goal sum doesn't change, so S2 is out. And then A1904, okay, so S1 is in, and then S0 is also in because that's the way this base case works. Okay, so I get the subset 4, 5 again. If I go down the right-hand side, okay, well, A39, A27. Okay, well that means the goal weight changed, or the goal sum changed, so S3 is in, because I'm at the point of view of, when I'm standing on A3 and I look backwards, I go to A27, so S3 is in. A27, so from the point of view of A27, the thing before it has a smaller goal sum, so S2 is in. A15 has definitely a bigger goal sum than A00, so S1 is in, and then I hit A00. So this is that special base case for k equals 0. So A00 is the base case corresponding to the empty set. And of course, I don't need to include S0 to come up with a sum of 0. So A00 is true and I do nothing at that point. So that path corresponds to the subset 2, 2, and 5. And so notice that I was able to construct my subsets only with the results of the subset sum decision problem. I did need the results of the decision problem for every subproblem to do that, but I was able to just use that and to look at the relationships between subproblems as a way of constructing my subset. I did not have to design a separate algorithm just to compute the subset itself. And so what this is telling us, of course, is that as long as I can keep track of the results of each subproblem, and I'm saying this, I mean, we obviously know this, but I'm saying this to remind us that we have to actually design an algorithm at some point here. As long as I can keep track of the results of each subproblem, I can solve my original subset sum problem just using all of this information here. So now the question is, how do we turn this into an algorithm? Okay, one conclusion I hope you can agree on at this point is if you get this graph that's been, pre-filled with all the truth values. Once you have this graph, it's pretty easy. That is, I can work my way down the graph, so I can, and as I work down the graph, I keeps going down. So it's pretty clear that if I begins at the value of n minus 1, that working my way down the graph is a linear time operation in n. So hopefully it's clear that if you have the luxury of having me hand you this graph with the truth values already in there, then it's pretty easy to get the subset. And even if the truth values aren't in there, you can compute them using a topologically sorted ordering of vertices. The question is, how do you get the graph? So if I wanted to, if you gave me a particular combination of a set S and a goal sum W, I could go build this dependency graph by working backwards from my goal state recursively using the recurrence. The problem is building the graph could be complicated. Now that's in 2 ways. One, I have to make a bunch of vertices and add edges and stuff, and that could take time, and I could need extra data structures to keep track of all the vertices. But 2, if I'm not careful and I go trying to enumerate the vertices that I need recursively, I actually have to be very careful with doing this, because if I'm not careful, careful, I might actually get this big exponential explosion of overlapping subproblems just from building the graph. I have to be very careful, for example, not to create the node A17 any more than once, because if I do, then I've got the same problem I had with my initial recursive Fibonacci algorithm. So I guess what this is telling us is that creating this graph is possible, but it might not be ideal if there's any way I can avoid it. And I want to be very careful with this point, because there could be some algorithms. There is a way of constructing the graph without the exponential explosion. It's just that I have to be very careful about doing it. So this warning here isn't telling me that it's impossible. It's saying that the obvious algorithm of just expanding everything recursively isn't going to work. I need some extra data structures to make sure I'm not accidentally generating vertices any more than I need to, any more than once per call to A. And there are particular problems where my recursive decomposition is complicated enough that I would actually rather just build the dependency graph. But this isn't one of them. And basically my illustration is this. So if I go and look at my dependency graph here, I've enumerated the subproblems that are needed to evaluate A39. But we can imagine there are other subproblems that could exist. So what about A25, for example? Well, I could evaluate that. I mean, that might depend on, I don't know, like A15. And A15 actually would depend, oh, actually A15 is already on the diagram. It's down there. A25 might depend on A13, for example. And A13 might depend on A03. And you can see that I could actually build in all sorts of subproblems that I never need. I don't need A25 anywhere in the solution to A39, but it could exist. And then I ask myself, what is the complete set of subproblems that could exist, even the ones that I don't need? So for example, there's also A21, and there's also A28, and things like that. And what I realize is that, okay, well, the maximum value of I is going to be 3. I is going to be between 0 and 3. And the maximum value of k reasonably should be 9, because why would I care about subsets of size larger than 9? And what I notice is, for any given input combination with n things in S, there are at most this number of subproblems that could ever be relevant to me. Because as I said, if our goal is A39, then I know that A31000 is never going to help me. That clearly will never be relevant. I don't know which, I mean, if you ask me, will A15 be relevant? It's hard to tell at a glance, but it's possible because I is less than 3 and k is less than w. So I realize if I think of all the subproblems that are ever possibly relevant, there are at most this number, n times w plus 1, which corresponds to all possible combinations of I and k, where I is up to is less than or equal to n minus 1 and k is less than or equal to w. And so I also know that any particular subproblem ik depends only on subproblems jq, where j is less than I and q is less than k. I mean, we can be much more specific than this, but what I'm saying basically is anything on this, on a particular row of my graph depends only on things below it, essentially, and with smaller values of k. So here's an idea. Rather than spending a bunch of time trying to find only the specific subproblems that I need, so this is nice, this graph I've created is nice because it's only the subproblems that I need, but it might take time to find those subproblems. Instead of doing that, why not just evaluate A for every subproblem that could possibly be relevant? So all of these subproblems. Just build a table, which is that size, n times w plus 1, where index ik of the table stores the value of aik. And then I could just go cherry pick the ones that are actually relevant to me. So here again, we have a table of values. Oh, isn't it great that dynamic programming uses tables of values? Well, yes, this turns out to be quite convenient for us. However, I want to make it really clear that although a table of values is helpful here, there are problems I might want to solve where it is actually better to build a dependency graph. Because maybe the number of subproblems I need, notice how the number of subproblems I actually use here is considerably less than 9 times 4. That is, if I look at w plus 1 times n here, that's going to be 4 times, actually it's going to be 4 times 10, so 40 subproblems. There are 40 subproblems that could be relevant to me. I do not need 40 subproblems to evaluate this, although I don't mind doing a few extra if it saves me time constructing the graph. There are problems I could decompose this way, though, where the number of subproblems is absolutely ridiculous, in which case maybe it's better just to build the graph. So a table of values only helps us to a point. It is going to help us in this case, though. And that's why I thought it was so important earlier to make it clear that just because you could use a table of values doesn't mean that you have to, and it doesn't necessarily even mean that you should. It might be that building the dependency graph and looking at those relationships directly is a faster method, although in this case, the table will help us. Okay. So here's a table that builds the matrix using the recurrence. So you give me S and you give me W, and I assign some arbitrary numbering to it. I create a Boolean array with n rows and W plus 1 columns. I encode in my base cases, so there are my base cases there, basically. And then I do a nested loop that iterates over all values of I from 1 up to n minus 1. And the logic here is that I'm doing the same thing I did with the graph, where I start at low values of I and work my way up row by row. And then for every value of I iterate over all the values of k from 0 to w. And because I know that the expansion of aik depends only on values of a that have a smaller value of I, I'm guaranteed, because of the order that I visited the values of I, that by the time I get to aik, both of the subproblems that I need will already have been computed, so already have their results. And then I have this if statement here, and I want to explain that just quickly. So earlier I defined a special base case for the case where if I asked for like a of 5, negative 20 or something, I said, well, that's obviously going to be false. Okay, so in this case, where a is actually an array, I don't want to have negative indices. So what I do is I notice that the subproblem ai minus 1k will never have a negative value of k, because k is always going to be non-negative. I've actually set that in my loop condition. However, the subproblem k minus si, okay, well there are going to be situations where k minus si could be too small. So for example, if my current weight is 100 and the value of k is 3, okay, well then yes, k minus si is going to be negative 97. So the if statement there is just saying, look, if k minus si is greater than or equal to 0, then this subproblem actually could be true. If k minus si is less than 0, then we know this subproblem is automatically false, so don't even bother with it. So if k minus si is greater than or equal to 0, we just resolve into this recursive case. All right, so like in the earlier coins in a row problem, I now have a table of values that tells me whether a subset exists for every possible combination of I and k. And we saw that once I have that, once I know the result of aik, whether it's true or false for all my subproblems, I can work backwards to actually figure out the subset that would produce a particular value of a. So in this version where I'm solving the decision problem, I'm actually solving it in n times w time. And keep in mind that subset sum in general is exponential in n, so that looks pretty good, except for the fact that w itself could be a large number. But that's still a big improvement over a general purpose exponential algorithm. This actually solves that in the decision problem in n times w time, and it just returns the true or false answer for n minus 1 comma w. We're going to see in a minute that if I just return the table, so if I just take the matrix A, I can use the truth values in it, similar to what I did earlier with the dependency graph, as a way of reverse engineering the subset. So the question is basically, suppose I happen to know that A of n minus 1w is true, how do I go about finding the subset once I have this table of values? And the answer is actually, I do pretty much exactly the same thing I did earlier, I just have to learn how to read the matrix, basically. So this matrix represents all of the different subproblems A, I, K for every combination of I and K. And let's just try reading that off a bit. So let's take a look at, let's do A3, 4. What this is saying, because this value here is true, is that there is some way of computing a subset of these 4 things. So A3, 4 would be using weights up to and including S3, you can compute a subset with total sum 4. And it looks like that is possible. I could take 3 and 1. Let's try another one. And maybe I should point out before I say anything else that notice how in the matrix I've only indicated the true things, so the blank cells are false, just to make it easier to read. Okay, let's take a look at A13. A13 is true because it's telling me that using S0 and S1, I can make a subset with sum 3, which obviously is possible because I could just take S1 by itself. Let's take a look at A25. Okay, A25 is false. It's telling me that I cannot make a subset with total sum 5 out of these 3 weights. And if you brute force it quickly in your head, you will observe that that is correct. There is no way of adding any combination of 6, 3, and 1 that gives you the total sum 5. So each entry of the matrix is telling me whether a subset with a particular sum exists using a particular collection of weights. So what I can do is basically start at my actual goal, which would be in this case A48, which is telling me that I can make a subset with total sum 8 using all of these weights. I can start there, and I know it's true, so therefore a subset must exist, and I can use the recursive form to work backwards, and by process of elimination, by deduction pretty much, I can figure out the subsets. I can find one subset that gives me what I want, that adds up to 8. There could be more than one, but I will find at least one that does that. Okay, so this matrix shows for the sequence of weights S equals 6, 3, 1, 4, 9, the matrix for the case where W equals 8. And as I said, false values are not listed in the matrix. They're shown as blank cells. So since A48 is true, we know that there is a viable subset, and as in earlier examples, there could be lots of other options. We just need to find one of them. And therefore, our goal is to make a safe choice, to try and, in our deductive process, do something that will result in success without any uncertainty. And so one observation I can make right off the bat is, okay, A48 is true. That means there is a way of coming up with a subset with sum 8 using all of these weights. However, so is A38. A38 is also true, which means there is a way of getting a subset adding to 8 out of only these weights by ignoring S4. And I think to myself, well, I should just do that then. Let's just ignore S4 and go up and look at this. Is it possible that maybe S4 could have been part of a subset with sum 8? Well, possibly, but I don't care. I know that there's a way of getting a subset without S4, so let's just eliminate S4. Let's get it out of the way. So that's what I'm going to do. Now, it turns out S4 is 9, so there isn't going to be a subset. But even if there was a subset that contained S4, I don't care. If there's a subset that doesn't contain S4, I can eliminate S4 from consideration. Okay, so if I look at A48, I notice that it's true that one of the reasons it's true is because the case A38 was true. So it could be that A48 is only true because of that. It could be that the other recursive case was also true. But I know that what I could do is just revert to A38 and work from there. So I exclude S4 and I look at A38. I notice that A28 is false. What that's telling me is, that's saying there is no way of making a subset adding to 8 using only S0, S1, and S2. In a sense, it's telling me that S3 is indispensable. I need to include S3 in my subset or else I will not get a sum of 8. Okay, so I add S3 to my subset. And I realize that that means that this is true because this recursive case held. A of I minus 1, so I minus 1 here would be 2, and K minus Si, well, K is 8 and Si is 4, so 2 comma 4. And sure enough, yes, A of 2, 4 is true. So my goal now that S3 is included in the subset, my goal is going to become make a subset of these things that adds to 4. In other words, let's deconstruct A24. I notice that A24 is true, but A14 is false. That means there is no way to construct a subset with total sum 4 out of just S0 and S1. In other words, S2 is indispensable. So S2 must be added to my subset. And I hope you're seeing the pattern here. Basically, if the thing above me is false, then I have to include the weight that I'm on, the weight Si. If the thing above me is true, then I just decrement I and try again. I don't bother with Si, I just go back to I minus 1. So there is actually a pretty clear pattern that I'm following here. Okay, so I now revert to A13 because I have things adding to 5 in my subset. I want to find the remaining 3 out of a subset of S0 and S1. I notice that A03 is false, which means there is no way of adding to 3 using only S0, unsurprisingly, and that means S1 is indispensable. And then once I revert back, so of course, in this case it's 1 minus 1, and K here is 3, minus Si is 3, I actually get A00. And A00 is vacuously true because it's a base case. So since subproblem A00 is automatically true, it's the base case corresponding to the empty set, I can conclude that nothing else is needed, S0 can be excluded, and therefore notice that I in fact do have a subset that adds to 8. And I did this by a sort of a combination of reverse engineering the table and reverse engineering the recurrence. Because I did need the recurrence for this because I had to know, for example, in this stage here, I had to know I have to jump backwards to A24 because that would be the recursive case that applies. Let's try another example. In this case, the weights are 2, 1, 3, 5, 2, and my goal weight is 7. And I will lament here that I would like to do an example with 10 weights because I feel like it is actually quite tangible. It's actually not that difficult to take to get a subset of 10 different weights that adds to 25 or something, but I can't do it because I can't fit everything on the same slide, unfortunately. So here my weights are 2, 1, 3, 5, 2, and I want to add to 7. And I think it's the case that there are actually quite a few options for that. So here are different subsets that I can see that add to 7. I've got 5, 2, I've got this 5 and this 2, I've got 1, 3, 2, and 2. So I actually have quite a few ways of getting something that adds to 7. I don't care though, I just want one of them. Okay, so find a viable subset that adds to 7. Well, A47 is true, so there is a way of making a subset that adds to 7 out of everything. But I notice that A37 is also true, which means there is a way of doing it without S4, so I exclude S4. Now, as I just said, there are subsets that include S4. That's fine. I just choose not to build one of them today. I could try and do that. There are other algorithms I could write that do that, but I don't need that. I want a simple way of getting a subset. I don't want to find every possible subset. I just want to find one. Okay, so now I'm at A37. So it is possible to make a subset that adds to 7 out of S0 through S3. However, A27 is false, which means unless S3 is present, I can't get a subset of size 7, which of course implies that S3 needs to be included in my subset. Okay, so S3 therefore is in. Since S3 is in, it has total weight 5. The problem I'm now trying to solve is, can I create a subset with total sum 2 out of the remaining things? So I go back to A2, comma 2, which is this position here. Okay, so I look at A22 and I notice that A12 is also true, which means there is a way of making a subset with sum 2 without including S2, so I exclude it. I notice that A02 is also true, which means S1 is not necessary either, so I exclude it. And then finally, I look at A02. It's a base case. So A02 is true because S0 itself is equal to 2, and therefore S0 has to be included. And notice that I now have a subset that adds to 7. It's not the only subset, but I did get one. There are other ways I could rewrite the algorithm to find the other subsets if I wanted to. It's a good exercise to try it because this is the kind of problem that I don't expect that it makes that much sense even watching me do it with all these examples because there's just so many moving parts. So trying it out yourself, writing the code for it, writing the code for what I just did, and advancing your code to find other subsets, you likely would find that you understand the problem way more after you do it that way. So here's some pseudocode to construct the subset. In this case, just because constructing the matrix took quite a few lines of code, this is going to take the matrix as an argument. So the logic here, of course, is don't call this function if a subset doesn't exist. And you can see the function will complain at you if you do. You can't construct a subset if no subset exists. So this takes a table of values A, computed by the earlier algorithm, and then basically formalizes the process that I just showed. So it just works backwards from AIK, or AIW, or I guess, sorry, an-1w, it works backwards from the lower right corner of the matrix and builds the subset as it goes. And it basically follows the logic I illustrated, which is at each step, if ai-1k is true, well then I guess si is unneeded, so just decrement I. Otherwise, si is required, so add si to your subset, and then adjust k accordingly, and then also decrement I. Now, I begins at size of s minus 1, so n minus 1, if the size of s is n. And notice how at each step of the loop, I gets decremented. So the loop itself is actually big theta of n. This last if statement here is just a base case thing to distinguish between the two types of base case. So A00 is always true. And if you ever hit A00, nothing else gets added to the subset. However, A02, for example, as we saw in the previous case, A02 is only true in the case where S0 actually equals 2. And so what you have to do down here is once I is equal to 0, you have to figure out whether you're in this base case or this base case. If you're in the base case where k equals 0, you do nothing. If you're in the base case where k is non-zero, you have to add S0 to the subset to complete it. And so once we're done, though, in linear time in the size of S, we have computed the subset. And the algorithm, as the slide is saying, can only be used if a subset actually exists. You can't construct a subset if one does not exist. So this algorithm is linear in the size of S, and the earlier algorithm to compute the matrix A was big theta of n times w, which means if I combine those two algorithms together, I can now solve the subset sum problem in big theta of n times w time, which is a pretty big deal. As I said, no polynomial time algorithm in n is known. And you stare at this and say, but wait a minute, this doesn't look exponential to me. Isn't this polynomial? Well, it is polynomial, but not just in n. It's actually polynomial in n and w. And the problem is you have no control over w. So w is one of your input parameters. If I wanted to provide you a nasty input with a huge value of w, I could do that. So for example, what if w ends up equaling 2 to the 2 to the n? Well, in that case, this algorithm is not going to be very fast. So it is, in the event that w is reasonably small, in other words, suppose that you happen to know that w is big O of n to the 10, which is a pretty generous bound, frankly, if n is reasonably large. If that's the case, then this is polynomial in n. However, you're at the mercy of the person providing your input, because if they provide an input where w is huge, this algorithm is not going to be polynomial in the input size n. But it's true that in the case where w is reasonable compared to n, this algorithm is very fast compared to our exponential time recursive algorithm from lecture 12. There's one other thing that's hiding in the background here that we should be aware of, though, which is that this algorithm requires this amount of space, too. So it is n times w time, but it's also n times w space. And because that number can increase dramatically as w goes up, even in cases where w is reasonable, like w might be n to the fifth or something, you might need so much space that you can't do it. You might actually need so much space that you don't have enough memory in your computer to execute it. There are tricks you can use to make that, to ameliorate that a little bit. Like there are ways you can represent the matrix in a sparse way, or you can recompute the matrix a few times as you go. But in general, algorithms like this that use tables of values can result in a space explosion that can make them sort of impractical at relatively low values of n, just because of the fact that typically we have more of a limit on space than we do of time. So our conclusion, I guess, is that unfortunately, although we now have this faster algorithm for subset sum that takes care of quite a few cases, subset sum is a very hard problem in general. And the more that we attack it, I hope the more that we grow to respect how difficult it is. Every attempt that we make to solve it faster doesn't seem to get us there. Now, we're not done talking about this sort of the basic application of dynamic programming principles. I'm going to talk about that again in the next lecture for two applications on sequences, although I'm going to use strings of text instead of sequences because they're easier to think about. And then once we're done that, once we've seen a few examples of employing dynamic programming techniques on a variety of algorithmic problems, we're going to go back to talking about optimization problems over graphs. And the reason we had to talk about dynamic programming now was pretty much because some of our optimization algorithms we're going to create for graphs can be optimized by using dynamic programming.